So good morning, everybody. Just so that you know, there's a new version of David's presentation on the drive with updates. And also inside day 3, there's a movie that he's going to show today. So if you want to access that, that's inside the day 3 folder. And Han wants to make some clarifications from yesterday.
Yeah, so yesterday, I think I didn't explain very well. And we were talking about the lines with the flat bottom. And I didn't think we reached a very, well, let me take my mask, a very satisfying conclusion. But when you think about it, the line opacity is eta, this line ratio, times the continuum opacity, the continuum optical depth, right? And so even if you change this line opacity by a lot, it changes the continuum opacity by very, very little. And therefore, the source function remains almost the same because you change in depth a lot, in optical depth a lot in the line optical depth, but not in the continuum optical depth because there's such a large multiplication factor. So then you change source function very little, and therefore you have this flat bottom in the line. Now, this is another indication. This is not very natural, of course, because typically the line source function can also change on the line optical depth scale by quite a lot. So this is another indication that the Milner-Eddington approximation is a limited approximation because you define things on a continuum optical depth scale and not on the line optical depth scale. What I wanted to say, that's, I think, a more satisfying explanation.
Hi. Hello, good morning. I have a point. Okay. So today we'll spend the day trying to understand how we solve the radiative transfer equation. Okay. So it's there are a lot of papers in the literature dealing with this, actually dealing about how to solve the RTE numerically, okay? Because only in few situations, very little situations, you can do it analytically. Yesterday, Han was presenting one of those ways, which is actually the Milner-Eddington approximation, okay? So I will show it here as well. You will see that the way I show it is completely different than what he did yesterday. But there are other solutions, other analytical solutions, much simpler ones, okay? Depending on what you consider. But usually, in the real case, when you deal with the spectral lines in the photosphere, you have to solve the radiative transfer equation numerically using any of the methods that has been proposed since many years. No? So you can try them if you like. Actually, it's not that difficult to program the method itself in local thermodynamic equilibrium. What is more difficult actually is that you have to implement all the opacities and all these things, and this is really tedious, okay? So it's much better to use software that is already there, no? Like SIR and RH and things like that. Desire. But there is a lot of them, a lot of methods, okay? So, well, this is what I'm going to discuss today. So basically, I will talk about the model atmosphere. That is important. We have to define a model in order to solve the radiative transfer equation. I will present the formal solution of the radiative transfer equation. Okay, that will help us to understand a lot of things. And then I will tell you which are the 2 different ways you have to actually solve the RTE and present just simple solutions and simple diagnostics, okay? So just remember, this is the RTE in local thermodynamic equilibrium. We have this just a simple, in principle, differential equation. Actually, it's four differential equations which are coupled for Stokes I, Q, U, and V, with the propagation matrix and the source function, which is the Planck function in LTE. Okay. Remember that this tau is the continuum optical depth in this equation, and that all the thermodynamic, the dynamic, the magnetic, the atomic, and the geometric properties are all included here. No? So also remember that in this equation, in particular in the propagation matrix, you have these elements in the matrix where you have the different absorption and dispersion profiles for the component at rest, the red component, the blue component, and these functions are just a combinations of different Voigt and Voigt-Faraday functions depending on the number of splitted levels that you have when you have the presence of the magnetic field. Okay, so also remember that when we are in the isotropic case and there is no magnetic field, most of these functions are the same, so the propagation matrix is just a diagonal, and then you end up with the transfer for just intensity, okay, which was the first assumption that Han was assuming yesterday when he derived the Milne-Newton approximation, okay? And you have been practicing a little bit with that, okay? This is the simpler thing that you can do in reality. So let's then start, okay? So, well, solving the radiative transfer equation, you need a lot of ingredients, okay? You need to define very well your model atmosphere. For that, you need a lot of parameters. So all these physical quantities has to be specified at all heights, okay? So, and they will basically determine which is the optical depth at all those points. They will determine which is the value of the propagation matrix at all depths, okay? And they also determine which is the source function value at all depths. This is the case in local thermodynamic equilibrium. Outside local thermodynamic equilibrium, this is not so, because the radiation also affects these quantities. So you have to solve the problem iteratively. Well, in astrophysics, all these things is what we call model atmosphere, okay? What do we have in practice? In practice, what we have is temperature and electron pressure, okay? Actually, you could have temperature or gas pressure or other things, but you can always derive them with the equation of state, okay? You also need the microturbulent velocity, which is partly responsible for the Doppler width of the lines. You also need the macroscopic velocity. Of course, you need the magnetic field to describe it, and for that you need the strength and the inclination and azimuth. So yes, you need the three components of the magnetic field. This is very important because in practice you have to define your reference system in your radiative transfer equation, which is usually along the Stokes Q positive direction. So when you interpret your data, you have to be sure that the Stokes profiles that you have share the same reference system with your radiative transfer equation. You also need you sometimes need to include something called macro turbulence velocity, okay, which is adding an additional broadening to the spectral lines. I will show you later a little bit about this and why it is there. And well, and then you have your model here, which is basically all these quantities along the model, which is stratified in local thermodynamic equilibrium, okay? It's plane parallel, okay? So you can define all the quantities there. And the only thing that you can do is just to go to your radiative transfer equation, just try to solve it, okay? And basically that all this K, S, and everything is a function of optical depth in your equation, okay? And now the only thing that we have to do is to integrate this equation, which is apparently a simple equation, okay? There are differential equations like this, which are way simpler to solve. The only thing that is missing is that we need boundary conditions as for any other differential equation, okay? So we need to provide, which is the state of the atmosphere at the bottom and at the top, okay? Well, so we can already say things about how the solutions would look like just doing an initial analysis of the radiative transfer equation. I will show you just one single example about that. So imagine that in your media, your stratified atmosphere, you don't have velocity gradients. So the velocity is always constant. Okay, you know, in the solar atmosphere, that's not the case. So you have granulation and everything, no? But just imagine that velocity is constant, okay? Just velocity. The rest can vary as much as you like, okay? Well, if that's the case, it turns out that the solutions for the Stokes profiles have a very clear defined symmetry properties, okay? And that's important, okay? So just to check about these symmetry properties, we can just make a change, a parameter change in the equation, and we can decide that, for instance, my wavelength definition, which is the wavelength and minus the central wavelength of my spectral line, I will change it and I will just turn it around and say, okay, I will change the sign of this, okay? And then I will apply this change to the radiative transfer equation, and I can check what happens with the propagation matrix. For instance, you can see that initially you have this propagation matrix here, and then if you change this, you have this new propagation matrix where you have most of the elements are the same, except, for instance, this one with change sign and this one, okay? And also, and this is, these two elements change sign, okay? So, okay, good. Well, if there is no change in the velocity along the atmosphere, okay? We can find a solution to the RT instead of this one, just this one with the same change, and then the RT can be written like this, okay? With this propagation matrix prime, okay? So this directly implies these relationships between the different Stokes profiles, okay? So Stokes I, Q, and U are exactly the same, even though I have just flipped the wavelength axis, if you think about that, okay? The only one that changes sign is Stokes V, okay? So this is because the profiles are basically symmetric. Stokes I, Q, and U are just symmetric. You can exchange the wavelength axis, but the Stokes V is anti-symmetric actually. So, and this has some consequences, for instance, for a few proxies that some people use for studying the solar atmosphere in real observations, okay? So one of them is, for example, this so-called net circular polarization. I don't know if you have heard about this, and there are quite a few papers talking about the net circular polarization in sunspot and things like that, where they use these measurements to have an idea about how are the magnetic velocity field gradients in sunspots, penumbra, and others, and in other scenarios. Okay, so but if you consider this simple situation where the velocity gradient is constant, and you realize that the net circular polarization, which is basically the integral of Stokes P, is identically zero, just because of symmetry properties, okay? Just because of symmetry properties. So it means that if there is no velocity gradient in your model, regardless the variations in temperature, magnetic field, or any other quantities, the integral over wavelength of Stokes P will be always zero, okay? The only way to have net circular polarization in the solar atmosphere is with the presence of velocity gradients, okay? If you have passion back, you said? I think it's the same. Passion back, the same, no? No, it's the same. If it is symmetric, the splitting is symmetric, is the same. It's the same. It will not be the same with hyperfine structure, for instance, for sure, because you have different components, and I think, well, I think so, yes. But in Alti, in Siemens lines, this. Yeah, there might be, yes. But yeah, yes. But what I want to stress is that just looking at the symmetry properties of the RTE, if you assume that there is no velocity gradient, this true, okay? So there will never be net circular polarization, okay? So you may have some spectral lines that are strange, or they have different splittings, or maybe there it changes, okay? But in general, this is always valid, okay? And it is also important that in those papers where they study the net circular polarization in sunspots and so on, they try to drive to write down conclusions just looking at the net circular polarization. But actually that's very difficult, because as soon as you combine velocity and magnetic field gradients, this integral here can really change substantially. So it's very difficult to identify which is the real cause when this integral is different from zero, okay? But what is true is that if there is no velocity gradients, this is always true, actually, okay? So this is just a simple exercise of things that you can do with the radiative transfer equation without the need of solving it, actually, no? So you can learn about the properties of the solar atmosphere. And so I think you have data that from Hinode, from yesterday. I don't know if that data has Stokes B polarization. You can try to do it. You can try to just take a narrow region that takes Stokes B profile and then make the integral. Okay, just zoom over wavelength and see what happens. You will see that is zero or not, and you will see the difference, because when you look at the profiles, most of them are simple profiles that, and actually the integral is close to zero, actually, okay? So, and the direct meaning is that the velocity gradients are small, basically, okay? So, in any case, let's try to do to solve the radiative transfer equation, okay? So this was just something that we could do in a simple way. So let's try to solve it. So how do we solve the radiative transfer equation in practice? No? Well, so the first thing that we assume is that we have this homogeneous equation. So this simple differential equation, and we just try to solve it, no? Using math, basically. Next, we just define this linear operation, which is called evolution operation, okay? And we just make a simple transformation and define it, this operation like this way, okay? So we can represent or write down the intensity at a given optical depth as this linear operator acting over the intensity at another optical depth, okay? This is just math, okay? So for this to be a linear operation, it has to fulfill two conditions. The first one is that the optical depth is the same here. This has to be the identity matrix, basically. This is a matrix. Remember, all these bold uppercase letters are matrices. And the other condition is that I can write the evolution operation from one optical depth to another one as a combination of two of them, okay, where you have an intermediate step, okay? So this is just a math definition. This is how we start solving the radiative transfer equation, okay? And then I can just write down the variation of the intensity along optical depth as the variation of the evolution operator with optical depth multiplied by the intensity, okay? So this is simple to do. So I will explain later what's the meaning of the evolution operator and why we do it like this, okay? So all this has a physical interpretation, okay? So we can also write the equation that we defined before, this homogeneous equation, using the evolution operator like this, okay? So you can write down the variation of intensity as the propagation matrix multiplied by the evolution operation and multiplied by the intensity at two different optical depths, okay? And then you can compare this equation with the previous one, which is actually this one, okay? And you can find a similar homogeneous equation, differential equation, not just for the intensity, but for the new linear operator that we call the evolution operator. And this is basically this one. This equation is actually the same as before, but before was for the intensity, now it's for the O, okay? We can still play around with these tricks, and then we can write a similar equation like this, but for a different optical depth, tau prime, okay? Instead of writing it with respect to tau, we can write it with respect to tau prime. You will see that the position of these two is changed, and then you have a minus sign, okay? So far so good. This is just math, a little bit of math going around. Well, so the next step is the important one. So we can, in practice, use this new function, this new thing as an integrating factor, okay? So we can just multiply the radiative transfer equation, not the homogeneous equation that I was talking about in the previous slides, but just the real transfer equation by this operator, and when we can have this other one. So that's still simple. And then we can rewrite this equation like this, okay? Using what we have learned, how you move the things around, we can actually write down the radiative transfer equation like this, okay? And now we have the source function here, propagation matrix, the evolution operator, and also we have the variation of this quantity along optical depth, okay? This one, we can now integrate between two different optical depths, tau equal 0 and tau 1. And then when you integrate this equation, what you actually have is this so-called formal solution of the radiative transfer equation. And it is called formal because actually it has no analytical solution. You have to do it numerically. So it's formally speaking, the solution is like this, but doesn't help. Okay, so only in certain situations you can arrive to a real analytical solution. I will show you a couple of them, but basically this is the formal solution of the radiative transfer equation. And starting from here is when you use all these methods that are in the literature that solve this equation numerically, which is the DLO method, well, there are a lot of them. I don't know, Han knows them pretty well, probably. But and it's just how to make this integral. Basically, you have to make linear approximations and do it step by step, okay? So, but this is actually the formal solution of the radiative transfer equation. You can make a much compact form of this formal solution, which is here, just supposing a limit. But this solution actually tells you how radiation propagates through the atmosphere, okay? So you can have a look to this first term here. So you can see here, this is the Stokes parameters at some point in the bottom, for instance. So this operator just describes how the intensity varies with optical depth, okay? Because this is the intensity at one optical depth, and it will be just modified by the evolution along this path from tau 0 to 1, okay? And the second term basically describes the different contributions from emission at the various layers to the final Stokes parameter, okay? Because the source function is here. So you have to integrate over the two optical depths, taking into account the emission as well, okay? The source function. So this is actually why it's called the evolution operator, because it's somehow telling you how the radiation evolves. Okay, so now we can assume a real scenario, for instance, the solar atmosphere, and then you know that your boundary, your integration limits at the top of the atmosphere and the bottom of the atmosphere. But at the bottom of the atmosphere, you know, is the place where the optical depth tends to infinity. And when this is the case, basically this quantity is actually zero, okay? Because you don't see any photon coming from the bottom of the atmosphere. So because of that, you can actually write down the formal solution in a more compact form like this. No? And the only thing that you have to realize that is integral is not between tau 0 and tau 1, it's just from the bottom to the top of the atmosphere, and it's just a very compact form to see the formal solution of the radiative transfer equation. Okay, from here on, the problem has to be tackled numerically. Okay, there is no way to solve this analytically. I know there are some few papers trying to do it, but they are, I think, way too complex. And well, this is what I was telling you. So it's called formal because this quantity is actually not known. Okay, and what basically what I was telling you. So you need to do it numerically. Okay, so in the next slides, I want to show some few scenarios where you can actually solve it. Okay. So, but to further understand the formal solution of the radiative transfer equation, which I just presented, which is actually for the Stokes vector, we can go to isotropic case, okay? Where, you know, the propagation matrix is just the diagonal matrix. So you just can take just intensity, okay? And the equation can be written like this, okay? With the absorption, the intensity, and the source function, which is the Planck function, okay? And then you can write down this as a function of the absorption profiles and so on. And this is something that Han was yesterday deriving from the beginning, I think, no? So, but this is just the radiative transfer equation in the case of the isotropic case, okay? Well, if you can do the same exercise and trying to find a formal solution as we did before for the polarized case, okay? If you do so, you will find that the formal solution in this case can be written like this one, okay? So in this case, we have the intensity here, we have the integral between the bottom of the atmosphere and the infinite, okay? And this is the Planck function, and so on. And here, instead of the evolution operator, you have the exponential of this integral, basically, which is, in this particular case, in the isotropic case, would be the evolution operation, okay? And the basic meaning is that this exponential, what it does is to attenuate the emission, okay? This is what it does in practice. Well, you can also think that, well, then my operator that I was defining at the beginning, no, is just a generalization of this attenuation factor, actually, okay? I say, oh, okay. Well, I can compare these two equations, basically, no? I can compare this one with the previous one. I say, come on, my evolution operation should be an exponential. Remember, we didn't know how it looked like in practice because we didn't have any, so this is what it was written here. So we don't know what, how it looks like. So we can do this, I say, okay, this, oops, wait, sorry. So this one has to be like this. So, well, I can write it this as the exponential of the integral of the propagation matrix, blah, 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 okay? And then I will have a simple explanation to the formal solution, and I could then talk about the attenuation factors and so on. But, actually, you cannot be that, do that, okay? Because this is a matter of math. So there is a problem, and the problem is that these two matrices that you have here, they do not commute, actually. So you cannot perform steps like this, just comparing the two equations. So this is not true, okay? And since they do not commute, you cannot say that the evolution of the exponential is equal to the evolution of the propagation matrix multiplied by the propagation matrix, basically. So this does not hold. So this equation, when you assume that the evolution operation looks like this, actually does not hold at all, and it's wrong, okay? And the point here is that these two matrices do not commute, okay? But we can try to find scenarios where actually this commutes, okay? And this is how you look for simple analytical solutions to the RT in LT, okay? Well, this is what so there is more thinking behind these properties of commuting matrices. I think you can find them in the book, okay? I'm not going to explain that here because it's just math. But this is what I was telling, that in those scenarios where we can find that two functions commute, we can write the formal solution like this, okay? Otherwise, the formal solution has to be solved numerically. So the RT has to be solved numerically. No, there is no other chance, okay? Well, when those two matrices commute, okay? So one thing that you can do is that you can write the propagation matrix, for instance, as a constant propagation matrix multiplied by the function that depends on the opacity, okay? if you assume that the propagation matrix can be written like this, then the two matrices commute. So you can write down the formal solution like that one, okay? So can you think about some scenario where actually the propagation matrix can be written like this? After yesterday's class in the afternoon, when we had Han here talking to you? Millennium. Oh, good. What's the assumption behind millennium? Okay, so one of the assumptions, well, was, let's assume all the thermodynamic parameters and the physical quantities that describe the solar atmosphere are constant. So they do not depend on the opacity, on the optical depth, sorry. So in such a situation, actually, you can write the propagation matrix like this, because the propagation matrix is just constant. It's constant. So, and then you only have a function here that depends on opacity. So this can be done in the Miller-Ellington case, actually, okay? But before entering into that, because this is the next slide, okay? So I was just wanted to show you just a simple solution of the RT. This is why I have this here. So you can go to the literature. There are some numerical solutions described in these papers. So more formal solutions and so on. So you can go there. They are interesting papers. But actually, when you solve the radiative transfer equation numerically, in the case of LTE, basically what you have is what we were talking about. You start from your model atmosphere, stratified model atmosphere, where you have the temperature, the electronic pressure, in this case, the ionosphere velocity, the magnetic field, inclination, azimuth, all these quantities vary from the bottom of the atmosphere here, okay, up to the top. This is your boundary condition that you have to set. Actually, you set the boundary condition at the top when you solve the radiative transfer equation, but and then you just solve the RT, and what you get is actually the 4 Stokes profiles, which is the thing that we measure in the solar atmosphere, and you can see the I, Q, U, and V. In this case, they are really asymmetric. Okay, they are really asymmetric because you have changes in the magnetic field. You have Stokes V, so if you calculate the net circular polarization here, it is 0 or it is different from 0. So you never know because the size of the lobes is difficult. No, you have to do it to know if it is 0 or not. But just looking at the velocity, since you know there is a velocity gradient, it is actually not 0. It will be different from 0. Okay, always. This is the only thing that you have to do. Okay, and you see the asymmetries. You also see the shape of the profiles, which are like this way because of the shape of the absorption and dispersion profiles. Okay, and remember that these things are combinations of different absorption and dispersion profiles, and that split depending on the magnetic field and all these things. Okay, so that is what you get when you solve it numerically. This is the forward problem. Okay. Well, you have to add more things to the forward problem. And this is what I was telling you before. One of the parameters that we usually use also when we do the forward synthesis is this macroturbulent velocity, okay? I usually don't use macroturbulence already when you have high resolution. I think, in my opinion, personal opinion, I think it's not necessary to use it already. But in years ago, when we barely could resolve granulation, macroturbulence was an important ingredient because you had an additional broadening in your profiles whose source of physical origin was not clear, okay? And then we said, okay, the lines are broader, so I put a macroturbulence, okay? And the macroturbulence is something that you do at the end of your profiles. You define how much macroturbulence you have, and you define that this broadening is due to a Gaussian distribution, okay, and you just convolve your results, let's 4 Stokes profiles, IQUV, with this macroturbulence, and you just widen them. Okay. I wouldn't use it now with high resolution, but it was used in the past a lot. Okay. But this is an additional ingredient that you can actually use when you do the forward synthesis and also the inversion. Okay. Well, actually, this is the effect of the macroturbulence. Okay. So this IQUV. So you can see here the splitting of the line, for instance, in Stokes side due to the presence of a magnetic field. And once you put some macroturbulence, you basically wash out everything. Okay. You reduce the amplitude of your signals and you destroy some of the information. Well, you don't destroy it, you just so the macroturbulence is you say hinders the information basically. And well, do you know other systems that work as this one? I mean, as a macroturbulence, because Kevin was talking about instrumentation, about filters, no, about the spectrograph. And when you have a filter graph, you can have very nice movies from the solar surface, and the filter graph is not does not have infinite spectral resolution. It is something that is finite, so you can measure it. So it actually acts as a macroturbulence. It's something that you convolve with your data. So if the spectral resolution of your filter graph is not good enough, you can really destroy the information in your observations because of that. Okay, and it acts the same way. It's just it can be interpreted as a convolution. It's not that a convolution, no, but it can be interpreted as such. Okay. So, what time is it? Well, now I will try to find these first solutions of the RT, and up to now, I think if you have questions, is the right moment, because now I want to explain this part straightforward. It's only 4 or 5 slides, but maybe we have to stop in 5 minutes. So if you have questions about what I have been showing you, is the right moment. You have a question. Yeah, because it's something. No. Yeah. Yeah, probably. Yeah. That's good. I actually have to. No, I think it's minus there because of that, because it's growing then a lot.
I'm kind of late to the party here, but I'm a little familiar with like intensity profiles. When you with macro turbulence, you just kind of add, like, let's say you have a Gaussian, you just kind of add some width and quadrature to like other widths, and that widens the line. But with the 4 Stokes profiles, are you saying that you convolve each of the Stokes profiles with this like Gaussian kernel for macro turbulence?
I didn't understand the last part, but what you are telling me is that if you convolve IQUV separately.
I guess that's what my question is. Do you convolve each of the Stokes 4 profiles with this Gaussian? Okay.
Yeah, you do it separately. Yes.
Just clarifying.
It's actually, so it's a linear operation. You think about that. So you can, I don't know if, Kevin was explaining yesterday that when you do measurements, real measurements, you don't measure IQ, UV. No, you measure a combination of them. So you measure I plus 20% of Q plus 20% of U and then plus 40% of V. This is one measurement, and then you do another measurement with different percentages, then another one, and then another one. Once you have four, you can already determine IQ, UP separately, just doing the inversion of the matrix elements, okay? But you could have 13 or 14, doesn't matter. So you could convolve those measurements or deconvolve those measurements, okay? But if you think about that, it's a linear operation. So it doesn't matter if you do it in I1, I2, I3, I4 that you measure, or you do it in IQ, UV, okay? It's exactly the same. In practice, we do in IQ, UV, okay? In the forward synthesis, because we don't, well, yes.
Consider the effect of microturbulence.
So first of all is where is the Gaussian here?
Yeah, for now it's not there, but
You have something, no? Something which is a combination of absorption and dispersion profiles. Actually, is in reality is a combination of Voigt and Voigt-Faraday function, actually. Okay, but from the convolution point of view, you can convolve anything. You can convolve a square function, a profile, or whatever. The only Gaussian thing here is the macroturbulence, because we assume that it's just like Maxwellian or something like that. It's not Maxwellian because it's Gaussian, but we just assume it as a Gaussian convolution, okay? But there is no relationship there, no? So I don't understand really what's your doubt. I think probably you have a doubt there more behind or something, but you can do it. You can convolve it without any problem. Huh? Shall we continue? Everybody is ready? So I promise I won't show any more operations like before, okay? So, well, a very, very brief summary. When I was talking you about the only way we can solve analytically the reactive transfer equation is finding a propagation matrix, which can be written as a function that multiplies the propagation matrix. I'm assuming that this is constant, okay? And when you do that, you can assume that the different matrices commute, okay? So in that situation, you can try to find a solution to the radiative transfer equation, okay? So this is basically what is written here is a little bit more, maybe more difficult to follow. I mean, because of I have introduced this new matrix, but well, let's assume that in fact, you can write down the propagation matrix like that, okay? And then also assume, which is important, that this f is scalar function, okay? So it's just a scalar function. And then we can define this L like this integral, okay? So you can see the resemblance with the previous equations. And now you have a constant matrix multiplied by this function dt, okay? If you do this, you can find out that actually the matrix K and L, K is the propagation matrix and L is this new matrix, they commute, okay? This function commute with this one, and this is identical to 0, okay? Well, in this situation, we can look for that analytical solution. And then we are going to do also another thing. We are going to take the definition of the exponential like this. So this is just something that you can prove mathematically. So you can write down the derivative of an exponential with respect to tau as equal to the minus the exponential multiplied by the propagation matrix, okay? So with these two things in mind, you can go to the formal solution, okay? Again, but before that, we will also assume that the source function, which is the other element in the formal solution, is just linearly changing with optical depth, okay? As yesterday, Hans explained it very carefully, okay? So then, if you have this source function, and then you can cast the evolution operation with like this, you can find actually a solution to the formal equation, an analytical solution to the formal equation, okay? That analytical solution is actually the so-called, Rakowski solution to the radiative transfer equation, okay? When you use a Milne-Ellington atmosphere, which means that everything is constant along optical depth. Okay, in the formal solution, basically, what you have is this with the new exponential, because this is the evolution operation. You have the constant, you have the constant propagation matrix. You have the source function that is linear. This integral can be done actually by parts. So you know how to do it. You can do it. It's easy to do. You do it, clean, clean, and then you find that the solution is basically this one, okay? Which is the same, exactly the same that Han was presenting yesterday, okay? But in this case, we have arrived in a very different way, just using the properties, matrix properties. So using the matrix properties, and we have arrived to this solution from the formal solution of the RT, okay? So if you work out the elements of this equation, actually what you have, I think you saw this yesterday probably, what you have actually is the expression of the RT in terms of the different elements, okay? Like this, there is so this solution is very practical. It's very useful to see how radiative transfer works in practice. I mean, when you have to interpret data and things like that, it's very useful. I think every student in solar physics has tried to do it or have to use it at some point just to see how the polarization changes when you move the magnetic field vector and things like that. It's kind of the exercises that you were doing yesterday, but with the whole with polarization, basically, okay? So this is what I was telling. This solution is known as the Uno-Rakowski solution, okay? And you have 9 parameters in the case of the Milne-Ellington atmosphere, okay? You have 5 parameters that are so-called the thermodynamic parameters, which is these ones, the eta, Doppler width, damping, and the source function terms. Then you have also 3 parameters for describing the magnetic field vector, okay? And then an additional parameter that for describing the velocity of the in the atmosphere, no, of the plasma. And those are 9 parameters. You could add an additional one. I think there are million-ton codes there in the internet, actually, from some institutes, that they have also the macro turbulence. So this is an additional parameter. And actually, you could have even more if you assume or you try to fix, for instance, 2 different lines, or you assume things like filling factor, things like that Rebecca will explain to you this afternoon, all these things. And well, there is something that you have to realize here that is very important from the practical point of view, because, well, now you have an analytical solution, but you have 9 free parameters, okay? So when you solve the radiative transfer equation, you have less free parameters. So you only need temperature and density, the magnetic field vector, and the velocity. The only thing that you need. You have less parameters, and actually you can describe much better different Stokes profiles, no? So this is actually kind of counterintuitive, no? Because you have a simpler solution, but one of the things that you have to pay is that you have more parameters. So when you have instrumentation, when you have spectra and many points, that's okay. But sometimes when you have an instrument that only observes 3, 5, 6 wavelength points across a line, okay, and you have polarization and you don't have Q and U because it's noise, you would realize that you sometimes have 10 points, 10 real measurements, okay, but you have 9 free parameters. So you are really at the limit, depending on the kind of observations that you have, okay? So when you choose between solving RT for interpreting your observations or using the Millington approximation, you don't only have to think about the model assumptions, okay, but also on the practical point of view, if you can do it, okay, because sometimes you are really limited. And that happens in practice. So this is something that happens. In the case of, I tell you this because in the case of solar orbiter, for instance, there is a vector magnetograph there, and we have just 6 wavelength points, okay? And we do all the analysis with a Millington that has 9 free parameters. So you are really at the limit. So we are playing with fire, you say, but nobody complains so far. So, well, this is the solutions that you get in the Millington case, okay? This IQUV normalized to the continuous intensity. Looking at this plot, you can see what happens when you increase the magnetic field. So basically, you can see, for instance, in Stokes V, that you see some splitting of the line, actually, in Stokes V. You can see that the amplitude of the signal increases because the magnetic field increases. Okay. There are important things to realize, and things that you can play around with the Millington atmosphere is that when you change the magnetic field, Stokes I also changes. Okay. So you can still hear people saying that Stokes I is not sensitive to the magnetic field. Sure. So sometimes it's very insensitive, but it's changing as well. So when you change the magnetic field, you change the 4 Stokes parameters because they are coupled, okay? Another important property is that all these profiles are have symmetry properties, okay? So if you try to compute things like net circular polarization, things like that, in a Millington scenario, so it's nonsense, okay? So you have to be sure what you do. And well, this is a movie, actually very interesting movie, because in the Millington case, you can play around with this. They are very cool. Yes. So I think you can. So if I play here, it will run. No? I know. So you can actually see, you can do this kind of exercises. What happens when you have a vertical field, and then you increase the magnetic field strength, and then you incline it in one direction, and then you change the azimuth of the field, okay? And then you see how at the beginning, when you just increase the magnetic field strength, Stokes phi increases, and you also see the splitting in Stokes high very well. When you turn it around, you can see here in Stokes high how the peak component appears, okay? Because it's that component is just zero when the field is parallel to the line of sight, okay? And how these two parameters are just give an account of the azimuth angle. Actually, the azimuth is the only thing that you can actually determine from the Stokes profiles without having the need to solve the RT or something like that, because this just the proportionality constant between Q and U. Okay, so you have to learn these things, and these kind of tools are very interesting, and just for you to know what is going on. Okay, you can also see that well, this XY should be okay. Yeah, when you have Y positive, okay, you have Stokes Q just because of definition. Okay, so if you go to a sunspot in a telescope and you have Stokes profiles and you look at Stokes Q, and then you realize that Stokes Q is not maximum in the vertical in your map, no, or something like that, although you believe it's oriented with the solar north, then you have a problem of the definition in Stokes Q in your instrument. Okay, all these things are important to know. Okay, so but millennium is also a limited view. Okay, so I think we can change from the movie already. Okay, the millennium approach is also very limited in some scenarios. Okay, and now in the next 3 slides, I will show you 3 cases where we compare how a real atmosphere with real Stokes profile compared with a millennium case. Okay, this is very illustrative. This one. It doesn't cross zero, you mean? Yeah. I don't, it depends on the rest of the parameters. So maybe it's damping or something. Yeah, usually it crosses, but it does not need to cross zero necessarily, okay? But you have that in it's very normal. No, in Siemens effect, you get it all the time as well. In the Hinode data, you see that very often. I don't know. I will look at that. I will tell you when you see that Q looks like this. I don't remember the parameters I used for this plot actually, so I really don't remember. But you see this in real case. In Hinode, you see it many times. It's not strange. Yeah, but the idea we have of Q and U is basically the same shape always, no? It's 3 lobes. So actually this, for both, for Q and U. But well, I will check just in case. Maybe there is an error, but I don't find it strange. Yeah. So yeah, but I can check why. Well, this is actually something why this is useful. So maybe we can check it and look for the real cost, no? And there is a reason, I'm pretty sure. Okay. Well, anyway. So these real cases, okay? I will show you 3 real cases where you have a millennium and then you have a real atmosphere, okay? All these things I'm showing is based on simulations, okay? Because in reality, we don't know how it looks like in the sun. Well, we have inferences and things like that, okay? But all these plots are based on simulations, okay? So we know that the model atmosphere, which is in this case very strange, because simulations are can provide you this kind of fluctuations along the line of sight, okay? And in this case, you have just a model where you have a magnetic field, an inclination, an azimuth, and a line of sight velocity, okay? And you can see how the inclination, for instance, is about constant. It's fluctuating, but it's around here, no? So it's a field that is rather vertical, actually. You have also some azimuth, and you have a steep gradient in the velocity, no? It's doing some fancy things, but there is a nice gradient. When you take the radiative transfer equation and you do the forward synthesis in these profiles, without looking here, okay? Just you can think about, well, probably I have a very asymmetric profiles, no? Come on, look at the velocity. No, it's moving, the plasma is moving a lot, the magnetic field is changing quite a lot. So I expect to have real asymmetries in the profiles, okay? Actually, before I showed you a model, which was much more smooth, how to say, and the profiles were really asymmetric, no? And strange, okay? But if you do the forward synthesis here, you would just get profiles, which are the blue ones, okay? The blue ones, the black ones, and the black profiles, they are pretty standard, how to say, they look really symmetric, everything should be constant. If I don't know this, and I take this, say, come on, so I'm looking at a mid-Eddington atmosphere, isn't it? And actually I can do the exercise and I can fit the mid-Eddington atmosphere. I fit it. It's pretty nice, okay? I know from the simulations that, well, more or less I have something that I can compare with, but it doesn't look like right, okay? So this interpretation is not that straightforward, okay? Because the spectral line is not just the whole atmosphere. So you will see tomorrow, and this is the most important part of the RT, that the spectral line carries information from some layers. From other layers, it doesn't carry that much information. So you can say more or less where your spectral line would be formed in the atmosphere. Okay, these things have to be dealt with care always, but it's not like the whole atmosphere. Okay, we will go into those details just to understand how it really works. So far, this is a pretty nice example where you could doubt about your approximation or not. So looking at this, you don't know if you are doing it right, actually. Okay, so it's not that simple. So there are other scenarios. For instance, this one, where you here have a huge change in the velocity and a huge change in the inclination as well, okay? And here you can actually generate asymmetries, okay? Strong asymmetries in the profiles. So you can see in stores V and stores Q that you have these strong asymmetries. You can try actually to fit them with a mid-Eddington atmosphere. So this is a simulation. You take these profiles and then you put an instrument in front of it. The instrument will wash out all the information somehow. And then you will see that these profiles, they look like mid-Eddington as well, actually, okay? So this is the learning process. So you need to know when you can do mid-Eddington, when you cannot do that. I think Rebecca will show a lot of things about that. And these extreme cases, for instance, where, well, come on, this is I don't know if it is realistic or not. It comes from simulations. Maybe the solar atmosphere behaves like this, but in this case, you really have profiles with 3 lobes, a thing like that. And then the situation, you can opt for 2 different solutions. You can go to the RTE and try to introduce these strong gradients. That's not that easy. You will learn that this week, I think, with the SIR course. It is not that simple. Or you can even say, okay, I have 2 different atmospheres. So I use 2 profiles for the millennium, and then you fit this profile very well, actually, okay? And then you have to interpret that. Those things are really important. I think this is the most important things that you should learn in this school. I don't know if Rebecca agrees, but that's the real life. And well, the last thing I want to show you today actually is we have seen one solution, which is the millennium atmosphere, that you at the end arrive to this Ono-Rakowski solution to the radiative transfer equation. There are other solutions. So this is not the only situation where you can find an evolution operation that can commute, okay, with the exponential. You can assume other circumstances. For instance, you can assume that the magnetic field is constant, okay, like here. And then you can assume that you are basically observing along the magnetic field. So the magnetic field is pointing towards you, directly pointing towards you. And that helps you to simplify the radiative transfer equation, basically, okay? So then actually the radiative transfer equation is this simple, okay? So you have only Stokes chi and Stokes phi. You have only these 2 profiles here, IV and the Planck function, okay? And this is much more simpler. So just for the case when the magnetic field is pointing toward the observer, you can simplify it to that 2 differential equations, okay? Actually, you can compare this to the one that was the solution in the isotropic case, okay? It is this one. This is the one that you were using yesterday. And then you can try to find the formal solution in this simple case, okay? Why not? Let's do it. According to the previous 2 equations, just comparing them, we can write down these 2 quantities, which is the 2 equations, plus and minus, okay? I plus B and I minus B, like this, okay? Just to make more similar to the isotropic case. This case is minus and plus here, just be careful. And then this actually, since you're looking at a magnetic field that is pointing toward the observer, this just as you were looking to right-handed and left-handed circular polarized light, basically, okay? So, and you know that in the absence of a magnetic field, this is the formal solution. But when you put the magnetic field, the formal solution can be written like this one, actually. And now you can explicitly write the evolution operation here as an exponential. Okay, this is very important. These 2 equations are almost equivalent. Okay, so the only difference is that you have the right-handed and left-handed circular polarization here and here. The rest is exactly the same. Okay, and these 2 equations, one for I plus B and another one for I minus V, not for I and V, okay? In the particular case where you have a Zeeman triplet, okay, these 2 functions are exactly the same. Exactly the same, and the only difference is a shift between them, which is twice the lambda V. You remember? So just depending on the wavelength square and the magnetic field, you will have a shift. It's twice that shift actually, because it's in the right-handed and the left-handed, okay? It's between the blue and the red, or the 2 sigma components, okay? Left-handed and right-handed. And then when you write down, you can represent these two profiles, and you will see that the I plus phi profile is actually a intensity profile displaced from the central wavelength, okay? An amount given by the magnetic field strength, and when you represent I minus V, you have this one, which is the same line, shifted to the other direction according to the magnetic field strength, okay? When we do measurements, we actually, in many occasions, we just measure I plus V and I minus V. Many instruments, they are just longitudinal magnetographs, okay? And this is actually what they measure. They measure these two profiles. So if you remember the movie that we have been seeing before, when you increase the magnetic field longitudinal, you increase Stokes V, and you see the splitting in I, and the I splits in two lines, okay? So this is just basically, if you want to know what is high Stokes I here, you just add this plus this and divide it by 2, okay? And then your line will be the two components, left-handed, right-handed circular polarization, okay? If you want Stokes V, you just make this one minus this one, and then you have a nice Stokes V profile, okay? And it's a nice way to see how it works. And it's also a nice way to see because there are real instruments that do this kind of measurements in daily, okay? There is actually in Japan, in the National Astronomical Observatory of Japan, there is an instrument that just does these two measurements, I plus V and I minus V, continuously in a atmospheric line, I think, I don't remember the line, and it's just measuring these two lines, and they have an arrow filter here, so they can measure the intensity in one, the intensity in another one, and they can really calculate a lot of things, because when these two profiles show different velocities, you can actually measure the velocity as well, okay? When these two profiles are different in the residual intensity, you can measure the amount of, so how much circular left-handed and circular right-handed polarization you have relative, okay? And actually you can have a direct measurement of the magnetic field strength if you were be able to see the splitting of the lines, okay? Well, these simple cases where you can solve the radiative transfer equation, okay? In this case, you can do it, and you don't necessarily need to go to the full solution or the numerical solution. So you can interpret your observations directly from the data, okay? In any case, you can imagine that assuming that the field is longitudinal in the solar atmosphere is a very strong assumption, okay? This is not the real case. But still, it helps you to understand how you measure it and how you build instruments and how you can easily interpret the RT in local thermodynamic equilibrium, okay? So actually the next chapter, and it's the one that we want to deal with in the next 2 days, deal with that, how to interpret the Stokes profiles, okay? Not from the observational point of view, but from the theoretical point of view, okay? That's much more important, and it's much more fun. I don't know what time is it. I think we have still time. Okay, so I can start and then we can continue tomorrow, okay? Because this is the last, almost the last part of the radiative transfer, but it's actually the most important, I think the most important one, okay? So, well, up to now, do you have any questions from the previous discussions? Because we are going to change basically the subject.
I have 2 questions on the figure that you show on how the microturbulence affect the Stokes profiles. Could you go back to that figure?
Which
Maybe
one?
on the one that you show how the microturbulence affect the
Oh,
line
okay.
profiles.
I can go slowly. This one.
Yeah, one is for the stocks V profiles. Do we have some straightforward explanation for the little wiggles at the center of the stocks V?
This one.
Yeah.
Yeah, this how it's because how you combine all the different absorption and dispersion profiles. This is called the magneto-optical effects,
Okay.
which I think is maybe not the right name, because I find in the literature that some people put different names, but the explanation is just how you combine the different absorption and dispersion profiles. Okay, sometimes you have these effects.
Okay, and another question is that for microturbulence, you convolve the entire profile with a Gaussian, say. And I just wonder what's the difference when you just add another Gaussian component to the Doppler width, say. What's the difference that it might affect the final profile that you will get?
The difference is here. So because the Doppler width of the line goes into the absorption and dispersion profiles, and those profiles are not Gaussian. They are this so-called void and void Faraday function, okay? It's somehow a combination of a Lorentzian and a Gaussian function, okay? So the way you widen the spectral line is not exactly the same, because it affects differently in the lobes, in the winds, and in the core, no? But you could imagine that you could add the macro turbulence to the Doppler width there, no? But we already have that. This is the micro turbulence. Okay.
Okay.
So we also have the micro turbulence, which is supposed to be an additional broadening of the spectral line due to macro turbulence things in the solar atmosphere. Okay. So when I use SIR, I never use micro turbulence, only when I cannot really fit the profiles, because I think microturbulence does not have a real physical explanation, okay? Because it's just that you need an additional broadening to the central part of the line. And that could be the definition of the microturbulence when you put it in the Doppler broadening, okay?
Okay, thank you.
Just want to add to that comment that I believe that the dispersion profiles are the ones that cause these magneto-optical effects. So if you were in your Millennium, for instance, force them to be zero artificially, then you would get rid of those two little lobes in Stokes V. And they tend to appear when magnetic field is stronger. Yeah, they're somewhat proportional to the magnetic field. In fact, to the square of the magnetic field for Stokes V or something like that. I forget the relationships.
So no more questions. I will introduce tomorrow's. Okay. If I arrive. Okay, this is what we are going to talk about tomorrow and the day after tomorrow, okay? Which is the Stokes spectrum diagnostics, okay? Well, this is the main problem that we have, okay? Astrophysics. So how to infer all these physical quantities that we have been discussing about, temperature, the pressure, magnetic field, velocities, things like that, from what we actually observe, which is the Stokes spectrum. Okay, so we cannot measure these quantities in situ. Okay, we cannot go to the sun, although we are trying to do some of such measurements, no, like in the Parker Solar Probe, no, that is going really close, no, and trying to measure the magnetic field locally, okay, or the density of particles and things like that, okay, but not in the solar atmosphere. We have to use remote sensing there, okay. So for remote sensing, what we just measure is light. It's the light coming from the solar atmosphere, okay? And then this, what we need, we need a ruler just to translate the observables into physical quantities, okay? And this ruler is the RTE, the only ruler we have. But we need to learn how to use it, okay? A simple one is very simple, you put it in the desk, but the RT is not that simple. Because you need to know what are you doing and what you have there, how is all the information dealt with internally to know how to use that ruler. And in order to learn and to understand if you can believe your measurements, your physical quantities or not, okay? Because you can end up in situations where you have perfect fits and they are completely unrealistic, okay? So this is why this chapter is so important. Well, actually, one of the first things we do just to understand how to use this ruler is to simplify assumptions, okay? In the case I'm dealing with, we are in the LTE, local thermodynamic equilibrium. Everything is much simpler there. Non-LTE is way more complicated, and non-LTE plus atomic polarization and Hartley and things like that is even more complicated, okay? But you also assume things there, no? Just to try to use your ruler, no? Well, and one of the things that you need to understand how to do such a measurements is that you need to see which is the dependence that you have between what you observe, okay, and what you want to determine. This is what you were doing yesterday in a simple, very, very simple scenario. You need to know what happens when you change your damping, what happens in your Stokes profiles, your intensity, okay? Yesterday you saw that when you change, for instance, the Doppler width, I don't remember, no? The lines is broader, no? And things like that. That, when you have a stratified atmosphere, is a little bit more complex that just changing a parameter and looking to what happens into the Stokes profiles, okay? For understanding this relationship between observables and physical quantities, we will introduce several things here, but the most important one is the concept of response functions, okay? Because they provide you information about how the spectra and the Stokes profile react when you just touch any of those physical quantities, okay? What happens when I move the magnetic field or when I change the temperature, okay? The profile change, yes, but how to interpret it, you need some tools in this particular scenario because it's not that simple, okay? And those tools is what we call response functions, okay? Using those response functions, then you can understand how the line is actually formed along the solar atmosphere, okay? And then you can start discussing about things like line formation heights, or where is the information coming from, okay? This step-by-step process. And tomorrow I will start showing the first thing, the things that the solar community were using to understand those relationship between observables and physical quantities. And those are these so-called contribution functions. That is something that comes directly from the formal solution of the RTE. And that contribution functions were at some point used in the solar community to understand the measurements, but actually they are not valid because the theory was misinterpreted, actually. So, and then we had to move further and introduce these response functions, okay? And actually the response function is the core of any inversion code, okay? Because for an inversion code to work properly, what it needs to know is how to change the model in order to fit the observables, okay? And for that, it needs to know how the profiles change when it changes the physical parameters, okay? And all these things are, everything is here connected, okay? And well, so well, I have more things here, no? This is what I wanted to discuss tomorrow. That basically, what we see is stock size, is intensity, and then we see polarization, and the polarization is state of light. And we want to know things like, are the photons at different wavelengths coming from different places in the solar atmosphere? Are they coming from the same place? Are they related with the same state of the plasma, temperature, density? Okay, so we will start discussing this from the simpler isotropic case where we don't have polarization, okay? And this is what I want to start with tomorrow morning, okay? I don't want to start now because it will take kind of half an hour to explain the basic building blocks of all these things, okay? So it means I will stop, basically. I don't know if I have to stop right now or in 5 minutes, but if you have questions or something. 5 minutes, okay? No questions?
So if you can go back to the slide where you showed Minley-Eddington results to a simulated atmosphere.
Like,
Yeah,
Please
one
go.
of these, yeah, any of these. So maybe the very first one where you showed that V is actually symmetric. So we have line of sight velocity gradients. It should the net polarization in V should not be zero if we have line of sight velocity gradient, but you showed in one example, maybe this one or the very
No,
first one. Yes,
the first
yes,
one.
yes. So means is it because of the simplification in Minley-Eddington, or maybe
No, this is just this is what is this school for, I think. So you need to know what how do you interpret your data. The net circular polarization is something that has been used many times. Okay, you go to your data, you just calculate the integral, your Stokes profile. Okay, you zoom this, and you say, okay, if my INCP is equal 0, I don't have velocity gradients. Okay, but actually
it is
maybe it is small, but here you can see that you have a very strong velocity gradient. Okay, you could you could interpret that from here. In reality, not all the atmosphere is contributing to Stokes V. It's only part of it. don't know, maybe this part, maybe this, or maybe this. We will see tomorrow, okay? So it's only a small piece of the atmosphere. Maybe that piece of the atmosphere is this here, okay?
Mhm.
And then the velocity gradient is pretty small, and this is why your CP is almost zero, okay? So you could say that you don't have velocity gradients, okay? And this is how you have to interpret things, always carefully, okay? So in this case, actually, I think probably is a fair interpretation. I don't see NCP basically because in the part of the atmosphere where the line is coming from, or where we have most of the information, the velocity gradient is small enough to be detected in the observation that I have, okay? But all these things are the things that you have to learn, actually.
And also maybe because this Miller-Eddington gives us just maybe one kind of average.
Exactly. So
Scenario.
The Miller-Eddington gives you an average or a center range. Maybe is this average here?
Okay.
Okay, maybe not. I don't know. I don't have the tools now to see where I'm looking at.
Okay.
Okay, I will show you tomorrow those tools actually.
Okay. Yeah.
But here you don't know, because actually maybe here, but sometimes maybe here. Sometimes maybe here, sometimes maybe in the bottom or in the top of the atmosphere, because all these things are actually model dependent. So they are not unique. So this is what Han was saying yesterday, I think, that there are studies there that say the iron line, blah, 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 is formed at 300 kilometers. I say, okay, good. So, well, probably it's around those heights is where most of the information is coming from. But actually it depends on where are you looking at, but it's model dependent, okay? So, but it could be the same thing to say the iron line is formed deeper or the mid photosphere or in the upper photosphere, okay? Because the error bar is so large that you can really say it more.
Precisely.
Yeah, it's more precise to say, well, it's coming from the deep photosphere or from the upper photosphere. 300 kilometers, 300 kilometers. There is no, but we will see those things, okay?
Okay. Yeah.
That's the.
So this discussion actually got me thinking on what you mentioned about, for example, Inton being used in sort of orbiter data, stuff like that. And now I'm curious about how do you then constrain how accurate these results are? If from what we're seeing up until now, I feel like this seems like a very good fit. So if you're doing like some statistical fitting, you would say it's good, but then the results that we're seeing here comparing to what the actual field values or azimuth velocity is are kind of like maybe off. So how do you then constrain it to get like some accurate scientific values?
That's a pretty good question. I think this afternoon with Rebecca, we should discuss about this. I don't know, so the answer can be half an hour. But I would say first, and this answer maybe is not expected. So the answer depends on who is asking, okay? It depends on who is asking. If you are talking to helioseismologists, okay? Solar Orbiter has one of the main science goals is helioseismology, because we are going to look at the poles. The helioseismologists, they want a precision in the velocity measurements. I think I remember it's 3, 4, or 5 centimeters per second or something in the velocity, or meter per second, I don't know. Ridiculous. It's really ridiculous, okay? If you show them this, they actually, and we have done that. I can tell you we have done that in practice, okay? With some of them, they look at this and they say, I don't understand anything. What are you talking about? So these kilometers, error bars. So this has no sense. So what we do is we go to an assumption that fits to the helioseismologic way of thinking. And we do the numbers and say, okay, if I use this simple model, I can tell you that from the intensity profile, I can determine the velocity shifts with a precision of 5 meters per second. And they say, oh, okay, I buy it. I say, perfect. And then you give errors based on those things. And you say, okay, my systematic errors are these ones, my random errors are those ones, and everything is then built up from the bottom to the top. In reality, if you look in the real physics, you know that the error bar is much larger, okay? So it depends. If you talk to people that do extrapolations, okay, they also have their own problems, no? They actually do things that are, for some people, it's counterintuitive. So the first thing that a guy that does extrapolation, you provide him a 4K by 4K image of the sun with a very high resolution and very nice. And they say, oh, it's too big. Let's go down to 10 arcseconds. I say, come on, you are destroying all the information. And then they take the magnetogram at 10 arcsecond resolution and they start to extrapolate things from there. And they also say, which is your error in your magnetic field values? And you say, I don't know, because you have been doing so nasty things to the data, but I really don't know. So you are missing everything. You are missing everything there. And Rebecca will talk about that. But they say, okay, but I need to know those numbers, okay? So you do also simple assumptions, a little bit more complex than in the case of the helioseismology, and you calculate those numbers, okay? You provide them and they use all these things to do the physics. So is it wrong? What are we doing or not? It's not wrong, okay? Depends on what you want to do with the data that you have. So it might be sometimes really unreal or look like something unrealistic, but those things actually work, okay? And now in Solar Variability, we have another problem, which is very interesting, and we are dealing with that right now. It's the first time we do stereoscopy with the magnetic field, okay? 2 different views of the sun for a stereoscopy. And the people is asking, which is your error in the stereoscopy? And then the helioseismology approach doesn't apply because it's only velocity. The other one doesn't apply as well because it's just for single view. So we are trying to find out a way to tell the people that what we do when we do stereoscopy works because we can determine the magnetic field orientation with that precision when we are looking at 0 degrees and at 60 degrees. Okay, so you ask to me, you don't have to. I know the things. Okay, I know that we have a lot of uncertainties when we measure physical quantities in the sun. But on average, sometimes statistically speaking, or in particular cases, they are quite reasonable, okay? The important thing is that you should know what are you doing. You should know that your assumptions are valid, and you should know that you are properly using your tools, okay? And this is it. So this is actually not long answer, but maybe. Yes.
When I look at those plots, I go like, oh my God, that's so bad, right? Because you have these flat things while the field does everything. But I don't know if you stressed this already. Those lines on the side, on the 4 panels on the right, give you 1 point or a short amount of points in the x-axis of the left.
Exactly.
Right. So that is, so actually it's not that bad. You do at tau minus 2, log tau minus 2, you get something which is very similar to the real value. So I think that's pretty good.
Yeah.
That
but
was
this
just my comment. Because the first time I said, whoa, that's, like.
No, and this is why we use more lines, not just one. And this is why, so this is something that we have to work out these days, okay? But this not, we cannot do that in the real sun, actually. In the real sun, you just measure things and that's not that straightforward. So it would be very funny to have also the models. But this is not the real case. Yeah. But we will know, I will explain that in detail. Thank you. Anything else? Any volunteer? Something that I can answer with a single word?
Sounds like no. So there's coffee break now for half an hour, and Jana brought some pastries and some cookies. So thank you, Jana. So there's a change in schedule. Apologies for that. Kevin is not quite ready yet. So I'm going to do the late afternoon lecture on spectral line inversions, and then Kevin will come and do his 2 lectures back to back in the afternoon. All right, so this is what I called my talk, because it's really not about the details of the algorithms of spectral line inversions or anything like that. It's more about what are the practical problems and caveats and behaviors and idiosyncrasies that you're going to find when you use spectral line inversion codes, particularly the types of spectral line inversion codes that we're going to be using this week and next week. This is by no means comprehensive at all, but I just wanted to, let me see if I wanted to point out, this is really hard to use. I'll get there. 3 things. Those that first link is actually a recording. Thank you. From one of the deepest schools that NSO organized, in particular the Milne-Edenton School. I think it was the 3rd school, and it's just a brief, nice introduction to inversions that Ivan Milik ran. So almost an intuitive approach to what the word inversion means. So I would recommend it. It's a short lecture. The other 2 are 2 review papers that are talking for the most part about state-of-the-art inversion techniques of different kinds, and they're good reviews. So if you have interest, definitely go. That's where I would start. Yes. All right, so this is my outline. I'm going to start with just some concept definition reminders, what the forward problem is, what spectral line inversion is, generalities. I'm going to talk a bit about the merit function. And then I'm going to go into what I'm calling the idiosyncrasies of spectral line inversions, the practical problems that you're going to encounter for sure. All right, the forward problem. Given a physical state of the sun's atmosphere, given a set of known parameters, physical quantities, temperature, density, pressure, magnetic field, velocity, you name it, we in principle know how to solve the radiative transfer equation in order to obtain the Stokes spectra. Now you can make a bunch of different assumptions to solve your radiative transfer equation. Yesterday you saw the Milne-Edenton approximation with Han, and you actually saw it this morning with David, by which with a very stringent set of assumptions and simplifications, you get to an analytical solution to the radiative transfer equation that allows you to compute the Stokes profiles from a given set of physical parameters very fast and very robustly. The other extreme that we're going to see next week is the case of non-local thermodynamical equilibrium, non-LT, where now in order to solve the radiative transfer equation, well, it's no longer analytical by all means, and you have to solve the radiative transfer and the statistical equilibrium simultaneously and self-consistently in an iterative manner to go from the physical state to the spectra. Just for sort of broad reference, you know what the radiative transfer equation is, the equation that tells you how light propagates through a medium and gets absorbed, emitted, and scattered as it travels through the medium. The statistical equilibrium equations, on the other hand, tell you the properties of that medium, tell you how many atoms and molecules in each excitation state and in each ionization state there are at every step of the atmosphere. But in general, this is the forward problem. You have a physical state, you solve the equations, you get to the spectra. Of course, what we want to solve is the opposite. It's like from a set of observables, this is Stokes I, Q, U, and V, typically at a given number of wavelengths throughout a spectral line for the most part. What you want to know is the physical conditions in the atmosphere where that light was generated. You want to know the temperature, the density, the magnetic field, blah, 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 in each one of the pixels in your observation. And this is what we call the inverse problem. And in general, it's non-linear, non-unique, and non-orthogonal. And let me explain these concepts. I mean, you probably get them, and you've talked a little bit about it this morning. Non-linear refers to the fact that one given observable, let's say Stokes I, could be very sensitive to one given physical quantity, let's say temperature, in one part of the physical quantity domain, and could be completely insensitive to changes in the temperature in a different part of the domain. Non-unique is almost self-explanatory. It means that for a given set of observables, there could be multiple combinations of the physical quantities. There will be multiple different physical states that can produce those observables, either identically or similar enough that you could not tell them apart with your noise and your observations, etc. So this is a degeneracy. Different physical states produce the exact same Stokes profiles, and you can't really tell them apart with just the information from the Stokes spectra. And this last one is maybe a little bit nuanced, but also related to degeneracy, the non-orthogonality that David was talking about this morning. There's no single physical observable that depends on a single physical parameter. They're all this cross-talked amongst each other. So you can never solve just, go from temperature to Stokes I only or things like that, or vice versa. It's just a reminder, but when we extract information about the sun's atmosphere through inversions, we're not measuring the sun, of course, we're just inferring its physical properties. So we measure photons and we infer the physical properties of the sun's atmosphere. And that inference, the quality of that inference, depends on many different things. Of course, it depends on your measurement errors, right? If you have photon noise, well, that's gonna limit your inference capacity. If you have low polarimetric sensitivity and your Stokes profiles are always below the noise level, whatever it is, you could have instrumental biases or effects that you don't know and you don't account for, that will have an effect on your inference, on your physical inference. That inference also depends on what I don't know why I call it like this, you're measuring tape. Like, what spectral line are you using to, what spectral line are you observing that you want to use to infer the magnetic field, for instance? Like, is it magnetically sensitive? Is it very magnetically sensitive? Does it form in the photosphere or the chromosphere? Right? And then your spatial, spectral, and temporal resolution will affect your inferences and the kind of interpretations that you're going to be able to make. And lastly, I think another one that's really important and that has been stressed out in the past couple of days is your modeling assumptions. How are you going to interpret these observations? Are you going to assume a mean length and approximation? Are you going to be more sophisticated? Are you going to do a weak field approximation to obtain the magnetic field and so on? So any approximations that you make in order to do the interpretation of your spectra are going to affect your results and how much you can rely on them. All right, so this is actually not an algorithm really, but I want to point out that for spectral line inversions, we think always need at least 3 ingredients. Of course, you need some observations that you want to interpret. You need a forward model, so you need a set of assumptions by which you're going to solve the radiative transfer equation, essentially, that gets you from a physical state to some synthetic spectra. And then you need a metric to compare, in one way or another, the observations with the synthetic spectra. And I say this is not an algorithm because, for instance, if you talk about machine learning inversions, this comparison doesn't happen directly, but I'm not going to go into that. Even Milic is going to go into that next week. So since the first spectral line inversion codes were developed decades ago, people have come up with many different methodologies to go about this spectral line inversion problem. And I'm not going to talk about any of them. You'll get a lecture about machine learning based inversions, particularly neural network based inversions. But today I'm going to be talking about everything that I'm going to show is going to be focused on what I call the traditional spectral line inversion techniques, which are inversion techniques that do some non-linearly squares fitting of the observations and the synthetic spectra. Yeah. Okay, so let's look at what the algorithm for these traditional inversion schemes looks like. It's very, very general. I'm going to say that all the inversion codes that you're going to be using in these 2 weeks are of this kind. So as I said earlier, you have a forward model where you have radiative transfer equation, you know how to solve it. So you start your inversion by giving it an initial guess to the model atmosphere. It's like, I don't know what temperature, pressure, magnetic field there is on the sun that generated the spectra that I observed, but I'm going to give it a guess. Let's say 5,000 Kelvin and 150 Gauss, whatever, you know, you give it a starting point. Then the, can't use this, okay. The inversion code will use its forward model module to solve the radiative transfer, calculate the synthetic spectra. And then you also, of course, have to give it the observed spectra that you want to invert. And the inversion will compare these two, the observed and the synthetic spectra. And it will ask itself, is this a good fit to the observations? If the answer is no, then the inversion code will tweak that initial guess that I gave it for the atmospheric model in an educated way, and we'll see what that means in a little bit. And then solve the radiative transfer again, obtain some synthetic spectra that hopefully are a better fit to the observations. It will compare them again, and it will do this circle iteratively with these educated guesses until it converges to some synthetic spectra that really match the observations that we gave the inversion code in some sort of least squares manner. So when you arrive at that point and you get a best match, the best possible match, whatever that means, between the synthetic and the observed spectra, the code will spit out a solution. The solution is, of course, not the synthetic STOS, but what you really want is the atmospheric model that led to those synthetic spectra that really look like your observations. So here's an example of what's happening inside a Milne-Eddington code in particular. White are observations, and particularly these are observations from Hinode, I believe, one of the 2 lines that Hinode observes. So this is an iron line that forms in the photosphere. And the red lines are the different iterations that the inversion code is going through as it's adjusting that model atmosphere to find a good fit to the observations. So you see it starts from that initial guess at the very beginning of the movie, which looks nothing like the observations, and eventually kind of tweaks things and eventually converges to something that looks like the observations. And of course, when that best fit is achieved there, is when the code stops and says, here's the atmosphere that gave me this best fit. All right, so any questions so far? Yeah, Lenny. So Eleni's question is, how much does the initial guess that you give the model matters? And we'll go into it a little later, but it does matter, because if you start in a point of the parameter space that bears no relation to the solution, the inversion code will most likely get lost and not be able to find a good fit. So yes, it does matter. So this metric to compare observations on synthetic spectra typically looks something like this. And I'm missing formatting issues, but I think the equation is complete here. This is what we call chi-square, typically is referred to as. And this is where the lecture that I pointed out earlier, that recording from the Millennium Decay School, arrives at this expression in a natural way. So it's this, it's kind of a nice, derivation of how you arrive at this. But this is typically the expression, sometimes with some additional terms here and modifications. But this is basically the expression that we use to compare synthetic and observed spectra. And it's essentially a sum over all the Stokes profiles, and then a sum over all the wavelength points of the squared difference between the observed Stokes and the synthetic Stokes. Now, see, the synthetic Stokes depends on this vector P. This is just a way of showing that the synthetic Stokes depend on the parameters of your model atmosphere. And then this could be like the 6 millennium parameters that Han showed yesterday, or you could have a depth-dependent stratification of all your physical quantities. But your synthetic Stokes will depend on all of those. And then there's typically 3 additional quantities that go into chi-square. This is just a normalizing factor typically, and it's number of degrees of freedom, whatever. And it's the number of Stokes parameters times the number of wavelength points minus the number of parameters, free parameters in your model, in your fitting model. Sigma is the noise in your observations, and it typically depends on your Stokes parameter and your wavelength, although people don't usually go to those details. And this is something that we call the inversion weights. I'm going to talk about this in a minute. Okay. Important things to note. Chi-square is a hypersurface, and it has as many dimensions as number of parameters there are in your model. So if your model is only a temperature, a scalar temperature value at one height, then it's chi-square is just a line. But we typically have many different model parameters, and this is just simply a very complicated surface in many dimensions. It quantifies the goodness of the fit. And it does this with one single scalar number, chi-square, because you're summing over all of this, it's just one number. So the larger chi-square, the worse the fit is, the smaller chi-square, the better the fit is. It's essentially almost like a distance between observed and synthetic spectra. And yeah, the whole inversion problem boils down to trying to minimize chi-square. And typically, pondered whether to put this in the lecture and like go into the Levenberg macro algorithm that is typically used for these kind of inversions, but I don't see it as something useful. You can look up that in the literature. But yeah, there's minimization techniques that find the sort of gradient descent in chi-square and what direction they need to tweak each model parameter to like find a smaller chi-square value. So that's what I meant earlier by educated guesses. These algorithms find the direction in which they have to tweak the model parameters to get a lower value of chi-square. So let's go into the what I really wanted to talk about in this lecture. So Eleni's question. So let's say that I wish I had I could write here. This vertical axis is chi-square. And let's assume that chi-square depends on one single model parameter. So chi-square is actually a line as a function of, let's say, temperature in the x-axis. So temperature value along the x-axis, if you can imagine those axes. And let's say you start your inversion with a guess for the temperature, 5,000 Kelvin. That's in this part of the chi-square line, hypersurface. The gradient descents in so minimization algorithm will be like, oh, if I move the temperature in this direction, chi-square becomes smaller. If I move the temperature in this direction, chi-square becomes bigger. So I'm gonna go along this direction and increase the temperature because this is giving me smaller and smaller chi-square values until it gets to here. And this big square is what it'll be like. Now, no matter what direction I change the temperature in, chi-square increases. So this is my solution. And that's the solution that the inversion code will typically give you. You start there. Of course, if you start at a different guess for the temperature that happens to be closer to the global minimum of chi-square, then you might end up in the real solution, right? So this is one of the things that you really want to be aware of with these types of inversion codes is that depending on where you start in the parameter space of your model, you might arrive at different solutions because chi-square is a very complicated surface that is not smooth, it's super rough, it has lots of local minima in different places, and you can get stuck in them really easily. And there's multiple ways to go to try to get around this problem and to mitigate it. And some of them are actually embedded in the inversion code itself, and you will never know that it's going on, but it's actually happening. But typically, one of the standard ways of dealing with this is like, I'm going to start my inversion many times. I'm going to do this inversion 100 times when you can afford to do this. I'm starting from different parts in the parameter space, let it arrive at all these solutions and pick the one that gives me the lowest chi-square value, period. That might be affordable if you're doing a millennium inversion, but once you get to sophisticated inversions, it becomes less and less affordable because the inversion process takes a lot longer to complete. Another way, or a way that you can use in combination, is to start from educated guesses. So we talked about the Doppler velocity this morning, and it shifts the line back and forth. You don't need to start with a velocity of 100 kilometers per second. You can start somewhere really close. You can determine the velocity almost visually, or just use it so very simple fitting, find the minimum of your intensity profile and start somewhere close in the parameter space to the real velocity. And you can do the same for magnetic field quantities. There's something called the weak field approximation that is a very, very simple operation on your observations that can give you a rough initial guess for what the magnetic field is. Sometimes it's also used as a research tool, and it gives you the solution, but that's not the point. If you want to start inversions from closer to the solution, you can use some tools like that. All right, second thing that I want you to bear in mind, inversion weight. So let's say that you want to observe, you want to invert the blue spectra, the crosses, and you have Stokes I, Stokes Q, Stokes U, and Stokes V for a spectral line. And let's say you give your inversion code an initial guess or whatever, doesn't matter, but it creates a synthetic spectrum that looks like the orange one, right? Whether it's from your initial guess or somewhere in the iteration procedure, it has that orange line. And of course, the inversion code internally is like, I need to compare the observations with my synthetic spectra. So of course, to do that, it will go and resort to chi-square. calculate chi-square and like, is this big or small? Let's look at the true scale of these Stokes parameters in reality, because now you sum in over the Stokes and you sum in over the wavelengths. So this is the actual true scale of those observations. And this is typical. Stokes I is typically 100 times bigger than Q and U. Typically 10 times bigger than Stokes V, right? So what's going to happen? And this is a question for you. What's going to happen, right? Who's going to be dominating the value of chi-square? Exactly. So when it goes and calculates this difference between the observed and the synthetic spectra, the residual is going to be totally dominated by Stokes I, which is fine. It will fit Stokes I eventually. And you think, well, it will fit Stokes I, and then it can go about trying to fit Q, U, and V. But it's not always like that. So what we do here is we add this artificial weighting inside chi-square, whereby we multiply Q, U, and V by some arbitrary factors, Q, U, I don't know, by 100, V by 10, to try to amplify these signals just in the expression of chi-square, right? We're not really changing the value of the Stokes profiles. We're just changing the importance in chi-square of these polarization profiles to make them as big as Stokes I, so that the inversion code doesn't neglect trying to fit them. It is sensitive to them in the chi-square metric. And by doing this, you're doing many things. This has many implications. You're changing the shape of chi-square essentially to start with. You also, when you have observations with noise, you're amplifying the noise of these spectra. Or alternatively, you're telling the inversion code that the noise in Q, U, and V is much smaller than it really is. And that has implications down the line. But this is a very, very common thing to do in spectral line inversions. So let me show you an example of why, after fitting Stokes I, you might still not be able to fit Q and U and V if you don't weight them. So let's say you have these observations, Stokes I on the top, Q, U, and V, all of them as a function of wavelength, and you go and try to invert them without weighting them. So now you don't, all the weights are equal to 1, meaning you don't multiply any of them relative by any arbitrary factor. And my inversion code, this was a Milne inversion code I used. I arrived at this solution. And what I saw is that it fits really well Stokes I, it fit really well Stokes V. They look like perfect fits, but Q and U, the blue line is the inversion fit, sorry. Q and U would not fit at all. It's like, it didn't care that they were even there. Why is this happening? If you go and look at the residuals, the I observed minus the I synthetic, and the Q observed minus the Q synthetic, what do you see here?
They're all the same order of magnitude.
They're all the same order of magnitude. So even with that perfect, seemingly perfect fit of Stokes I, the amplitude of the difference between the observed and synthetic profiles is equal or almost larger than the actual amplitude of the observed Q and U. And the same for the perfect fit of Stokes V, that the difference between the observed and synthetic is still larger than your observed Q and U. So we want to give more weight to Q and U in the chi-square expression to see whether that makes the inversion code more sensitive to Q and U. So my next attempt is I'm going to multiply Q and U by 1,000, see what the inversion code does, and keep the weights for Stokes I and Stokes V equal to 1. Right? So that. So those are my weighting factors for I, Q, U, and V. And this is what the inversion code comes up with. Now it's fitting really well Stokes Q and U because I've really told it to, be sensitive to them, but it's not able to fit I and V. So lastly, I found a different set of inversion weights that, really was able to get the inversion code to converge to a solution where all fits looked adequate. And I don't want to give you the impression that when you're doing inversions, you're always like looking at changing the weights for every single Stokes profile that you invert. That's not the case. But you want to be aware that these are tools that you use in inversion codes, and that I would say for Zeeman polarization in the photosphere, your typical inversion weights will be 1, 100, 100, and maybe 10. If you want to choose a set of inversion weights that works for everything, more or less. There's no such single set of weights. It's a little bit of an art. And you're just going to have to play with it to some extent. Questions? Yes.
I just wonder if you use the solution that you get from, you change the width and you reuse the solution as the initial gas to fit, then when you do not assign any weights, what would happen?
Honestly, most likely nothing, because you're not really changing the shape of chi-square. So you're not like finding a gradient descent that looks any different than what it did in the last iteration. I guess it depends on why the code stopped, right? If the code converged at a solution that is not good enough because it was still iterating and it didn't have enough iterations to fully converge, maybe. But oftentimes what happens with these codes is that, like, after, especially with a millennium, 5, 10 iterations, like, I'm done. I'm not able to improve chi-square. And at that point, I'm not sure that starting from the previous solution is actually going to get you anywhere.
Okay.
It could, but this is because of subtleties, right? It changes, where it starts with the Leavenberg-Marquardt lambda factor that we're not going to talk about here. So that could actually, move things a little bit through into a different part of the parameter space, and maybe just get you to a place where you might converge to a solution.
Okay, thank you.
Yeah.
So I have a confusion related to chi-square definition. So as you divide it by the pre-parameters by NF, like a normalization factor. So is it a chi-square or it is a reduced chi-square? And if it is a reduced chi-square, if the best solution should be when it approaches to 1, not the minimum.
Yeah.
So,
well, yes, exactly. It's a reduced chi-square, and the best solution is compatible with 1. You're right. This is, I'm talking from a general point of view, and that's still the kind of the minimum of chi-square that you can find.
Okay, so you mean in general, the chi-square is almost always larger than 1. It never approaches so close to 1 that going beyond 1 is not going to happen anyway.
It's a little bit more complicated than that, because once you put weights in, you throw that whole normalization off. So
okay.
I just put it in because you'll find it oftentimes in the literature that chi-square is normalized and it's a reduced chi-square and so on. But then we play with it so much and we put the weights in, and sometimes we add terms, regularization terms and so on, that eventually
Will not
it throws up the whole sort of ideal of that chi-square. If anybody has anything to add to this, because I'm not the statistician, mathematician expert on this, go with no. Oh, okay, so yeah.
I was wondering what's the relation between how can I put the weights and the noise? I mean, how it's like this thing about going, like, really put it a lot of weight, but I know that my data has a lot of noise, so how much I'm not fitting the physical.
That's also part of that art. And I'm gonna go into the effects of noise right now, but it's true. I mean, so the weights essentially lying to the chi-square about the noise level, essentially. So if you're, this Stokes Q here, which is pure noise, if you amplify it by a factor of 100, yeah, it's gonna totally dominate your chi-square. And the inversion code is gonna try to fit it as best it can. And then you're gonna get spurious results. And that's what happens when you try to fit noise. So there is a trade-off there. And then you might want to be, if you have a lot of like quiet sun data where your Stokes, your polarization is really low and often in the noise, you want to be smart about your weighting factors, or you want to know what they're doing to your inversion results. And then I'm going to sort of showcase a little bit this right here. So let's say that you have these observations. Let's try. If I use the mouse, then online people can see this, but it's kind of a pain. So let's say you have these observations that you want to invert. Stokes I, perfectly normal absorption profile, Q, U, and V look like the noise. And that's because they are. This is actually a synthetic spectrum that I created with a Milner-Edington model. And I just added some Gaussian noise to the spectra after the fact. But I created these Stokes profiles using a magnetic field of 0 Gauss. So there shouldn't be any polarization signal. This is a Milner-Edington approximation, only Zeeman polarization. So the underlying real spectra look like that, but they're noisy. Let's say we want to invert these noisy spectra. Let me do an exercise. I'm going to do the inversion many times. I'm going to do multiple spectral line inversions of the spectrum with many different realizations of this same noise level. And what I get, just got my inversion code, did it out of the box. What I get is this. So these are these colored lines are the best fits that those different inversion realizations were able to find in all cases. And in the case of Stokes I, they'll all look very similar. They overlap on top of each other with some like minor differences. And in the cases of Q, U, and V, spanel is Q, you can see that the best fit that the inversion finds in each one of these inversions is not a strictly 0 Stokes Q profile. And the same for U and the same for V. This means that the inversion code is going to throw out a magnetic field strength that is not going to be strictly 0. It's going to be whatever value. Okay. And this doesn't mean that the inversion code is doing anything wrong. Inversion code's sole purpose is to minimize chi-square. So if the noise is such that I can fit this noise profile with a little bit of a Stokes Q, I'm going to do that because that is that gives me a lower chi-square than not doing that. So the inversion code is doing its job. If I do this inversion many times, remember the observed spectrum is always the same one. The noise is a little different in each one of the inversions. I can do this PDF, a distribution of all the magnetic field strengths that I retrieved. And what I got in this particular case was that the average field strength that I obtained from this inversion is around 45, 50 Gauss. Remember, the actual magnetic field was exactly 0. This is just an artifact of the noise. The inclination of the magnetic field is just spot on 90 degrees. And this means horizontal to your line of sight. That's what that means. And this, I'm not going to go into it, but it has to do with the sensitivity to the orientation of the magnetic field that the linear and the circular polarization have. So when you have some linear polarization signal, synthetic signal, and of the same amplitude of your circular polarization signal, the field is going to be horizontal to your line of sight. Transverse. And that's the distribution azimuths that I got. Pretty much uniform, I would say. This, of course, depends, as we talked about on the weights. I don't have an example of that here. It depends also on the noise level. The larger the noise, it's a noise of 10 to the minus 2. Now my average magnetic field strength is more than 150 Gauss. This is pure artifact. I'm inverting noise. I'm getting 150 Gauss. If the noise level is lower, 10 to the -4 of the continuum intensity, then I get much closer to 0 on average. And these, for the reference, are the weights that I used in this particular case, 100 and 110. I use these weights because these are the ones that the Hinode pipeline data inversion uses for all pixels in the field of view. These are fairly standard values of weights. So that's why I picked those. Of course, if I go and inspect my spectra visually, I'm like, this is just pure noise. I can't see any signal here. Then I might tell myself, I'm not going to weight QNU. That's ridiculous here. I'm just amplifying noise. But you want to be aware that this is part of the inversion problem. Any questions before we move on? Yeah, Ryan.
So the sort of standard weighting that you said, the 100, 110, would that still be the case for both like on disk and near limb regions? Because surely near limb, you'll.
No, I would say that this case is for photospheric magnetic fields that are in the hectogauss range, if anything, if that makes any sense. Again, if you have very weak magnetic fields and your measurements are pure noise, then you probably don't want to use these weights. If you have very strong magnetic fields inside a sunspot, you probably don't even need to weight the spectrum because your polarization signals are going to be strong. It depends. I want you to take this with a grain of salt. There's no one single answer to this. But both the HMI pipeline and the Hinode pipeline use a fixed set of weights for all pixels. And they're typically optimized for active region type fields, for maybe plage kind of areas. And then what you're retrieving in quiet sun parts of the field of view is the interpretation of noise. That's kind of where I want to get with this. It's like when you take those inversion results that you didn't do yourself, and you know that this is the methodology, you want to know where your inversion results are usable and where they're not. And if you're inversing quiet sun with low polarization sensitivity or something like that, with this noise level, with these weights, you're going to get these fields, but they're meaningless. Don't extrapolate them. Modeling assumptions. You saw a little bit about this morning too. So this is a little bit of a repetition, but limitations of a forward model, I call this, and this is what I say is a repetition because David mentioned it. So let's say that you're going to use, so in your inversion code, there's the forward model, right? And you make some assumptions to solve your forward model. Let's say you use a Milne-Newton approximation to solve your forward model. You have a Milne-Newton inversion code. You know from this morning that when you use a Milne-Newton approximation, because you assume that velocities are constant, you will never get asymmetries in the spectral line. Simply, it's impossible to fit asymmetries in your observations. Alternatively, if you use a Milne-Newton code to interpret your spectra, you're never going to get information about your gradients in velocity along the line of sight. And this is just an example of that iterative process that the inversion code is going through in a case like this. So now you have, some observed spectra, the white ones. Again, these are Hinode spectra, nothing special. I might have got them from, I don't know where, Penumbra, I don't know. But you can see a very strong asymmetry in Stokes V. You can see that, Stokes Q and U don't quite line up in the same place. There's maybe less noticeable, but a strong asymmetry in Stokes I. And the Milne-Newton model creates this synthetic spectrum that is red, and it's either perfectly symmetric in the case of IQ and U, or perfectly antisymmetric in the case of Stokes V. That's the best fit that I can find right there. It can't do any better. It's just, you're never going to fit that. If you want to fit those spectra, you need to go to a more sophisticated model that allows for gradients along the line of sight. period. You might want to use the SIR inversion code that we'll be using tomorrow and Friday, for instance. So the modeling assumptions that you make, the approximations that go into your forward model are going to determine, to some extent, the results that you're going to obtain. And I'm going to limit them or whatever it is, but you want to know the context. You want to know what your modeling is assuming in order to interpret your results. Again, this is repeating the same thing over and over. You've heard this multiple times already. These are limitations. This is just another example, and maybe confusing today, but it's related to something that we're going to talk about next week. Polarization is not generated only by the Zeeman effect. There's other processes. And just for lines that form typically higher up in the sun's atmosphere and the chromosphere and the corona, polarization can also be generated by scattering processes. And what I'm showing here is Stokes-Q profiles, only Stokes-Q. These are synthetic profiles of calcium 8542, so chromospheric line, and they're the colored ones. Different synthetic profiles, no matter the details, but all synthesized with a magnetic field of 0 Gauss. Now, there is a linear polarization signal. This is not noise, but it's a real signal, right? There's a strong linear polarization signal, but it's not due to the magnetic field. But then I went and inverted it with the inversion code that does not know about scattering polarization. It's a non-LT inversion code that assumes that polarization is only generated by Zeeman. That's your model. Polarization is only generated by the Zeeman effect. It's a model. And the inversion code, of course, just wants to minimize chi-square. So it tries, the black lines show the inversion fits. It can't fit these signals. It doesn't have the physics in the model to be able to generate signals that look like this, but it still tries to minimize chi-square. So it still tries to fit a little bit, as much as it can. And that throws out magnetic field values that are not compatible with 0, just because it's trying to minimize chi-square. So it's an example of the same thing. Your model, you want to interpret your results depending on, you want to be aware of the limitations of the model. So another thing that came up this morning a little bit, David mentioned it in passing, the magnetic filling factor. All right, so these are two observations of the same sunspot, one from HMI, one from DKIST. And of course, I mean, this is not a fair comparison. Han is laughing, but it's, what you can see, of course, is there's way more detail in the DKIST image, as you would expect. But if you think about it, one pixel can't hold this steady enough, but one pixel in that HMI image, if you were to like look at it in this one, you're going to see there's a ton of small scale structure in the DKIST image that appears in only a single pixel of the HMI image. So the atmosphere, or the sun's atmosphere within a pixel of that HMI image is not constant in any way, not constant along the line of sight, but not constant in the spatial extent either. And people found, back when observations didn't look like this, they would do inversions and they're like, oh, man, I can fit Stokes high, but I can't fit Q, U, and V. There's no way I can't find a good model for I and V at the same time, or I and Q, U, V at the same time. So like, oh, but what could be happening? This is another addition to your model, but it's still a simplification. Let's say that this is, my formatting is off, but this is my resolution element. This is a pixel. Now, these people were like, okay, let's complicate the model a little bit and say, within my pixel, I can't resolve it, but I have a magnetic component and a non-magnetic component. And the magnetic component occupies a fraction of the total size of the total area of the pixel. So here this is what I call the filling factor. Filling factor is a factor, it's a model parameter now. It's a new additional model parameter that varies between 0 and 1. 0 means there's no magnetic component. It's all unmagnetized. 1 means it's fully magnetized. This pixel is all yellow. And anything between means I have two components, one magnetic and one non-magnetic. What does this mean in practice? Well, from this pixel, my Stokes I, my intensity, will come both from the magnetic and the non-magnetic parts of the pixel. And it's a weighted sum of these two, of the intensity of the magnetic and non-magnetic intensities. There, weighted sum. Filling factor times the magnetic component and 1 minus the filling factor times the non-magnetic component. The polarization, and again, I'm assuming Zeeman polarization here only and so on. The polarization only comes from the magnetic component. So Q, U, and V only emerge from this part of the pixel, not from this. So in terms of the fraction of area that they occupy, the observed polarization will be the filling factor times the magnetic polarization that comes from here. So let's do a thought experiment. Let's say you have 5 different pixels. And in each one, the filling factor is different. This is fully magnetized on the left and only 20% magnetized on the right. But the magnetic field in the magnetic component is the same in all of them. And let's say for simplicity that this is a magnetic field that's pointing towards you, so along the line of sight. Because it's along the line of sight, it will only generate Stokes I and V, but it won't generate any linear polarization. So what happens in this case is that the Stokes I profiles of all of these pixels are identical. The Stokes V profiles have all different amplitudes, but it's the same magnetic field strength in all of them. Okay. Let's look at it in a slightly different way. Kind of a very similar experiment. So you have 5 different pixels with different filling factors, but now each one of them has a different magnetic field strength, such that when I multiply these two quantities, they give the same line of sight magnetic flux density. So it's the product of these two quantities. How much magnetic field along the line of sight is crossing this pixel on average per unit area. And in all cases, this flux density quantity is 100 Gauss, but the magnetic field strength in each one of the cases is completely different. So the intrinsic field strength is different. The flux is the same, line of sight flux. So if I calculate Stokes I and Stokes V in these cases for all 5 pixels, I is identical. V is a little bit different in all cases, but now add some noise to these observations. You can't tell the difference at all. So you are going to invert these spectra, and you're going to arrive at a solution for the magnetic field strength, the intrinsic field strength, and you want to be cautious there, because that's not going to give you the magnetic field strength. The only value that you're constraining here is the magnetic flux density, because different combinations of intrinsic strength and filling factor are going to give you the same Stokes profiles. This is degeneracy. This is a great example of a degeneracy. And this has practical application in, when you're inverting quiet sun spectra with relatively low spatial resolution data, where you know that in the quiet sun, there's magnetic fields, but they might not occupy the entire area of your pixel. This is probably going on, and you don't want to interpret your results as magnetic field strength or intrinsic strength. Maybe close to, should finish now. There's a caveat to this. When you get Stokes Q and U signals, that can break this degeneracy, because the response of Stokes Q and U to the magnetic field strength is different than Stokes V. And when the fields are really strong, in the thousands of Gauss typically, also that breaks the degeneracy. But there's a regime of field strengths in the weak field regime where that degeneracy is pretty strong, and typically your Q and U signals are within the noise, so you don't have anything to constrain your solution. And this is my last slide, and I just wanted to mention it because I don't want it to go without mentioning, but the Zeeman polarization signals are very sensitive to cancellation of the polarization signals. So again, let's say you have a resolution element that is unresolved, right? Your observation is unresolved, your pixel is too big. It could have magnetic fields, again, in the quiet sun, magnetic fields pointing in different directions within that pixel. So in this particular case, I put half of the pixel with a magnetic field pointing towards you with one strength, and the other half of the pixel has a magnetic field pointing away from you with a different field strength. And these are the Stokes I and Stokes V signals that these two parts of the pixel generate. And what you can see is that a magnetic field pointing towards you and a magnetic field pointing away from you creates Stokes V signals with different polarities, such as when you add them up to see the polarization, the Stokes V in your pixel, they kind of partially cancel out. And when you take that final signal and you try to invert it, you get a good fit, and you get a magnetic field strength that might not be either one of the two that you put in, because there's been partial cancellation of the signals. So another thing to be aware of when you don't have fully resolved data, which is always, according to Matthias. Right, I think I'm going to stop here because, yeah, this is something that will be covered next Friday. There's a degeneracy, an absolute degeneracy of the magnetic field azimuth, where two different azimuth values give you exactly the same Stokes profiles. But this is something that Graham Barnes is going to cover next Friday. So I'm not going to talk about it. Any questions? Yeah. So Kurt.
I have one really quick one.
Yeah.
If you you go back, I guess one slide, two slides, one more. So this degeneracy, is there an assumption about filling factors in the Merlin inversions typically?
Yep.
For quiet sun, and is it different than, or do they do it in active regions, or is it only quiet sun? Because it only
No,
makes sense in
it's
quiet
always there. So there's no assumption in that. It is a free parameter of the model.
So the model fits to the filling factor that.
Yeah, it fits the filling factor between 0 and 1. It's a little more complicated than that in that it uses a stray light, so an average intensity profile, as a stray light factor kind of thing. And it says, I'm going to try to fit my observations with a filling factor times my magnetic component, and 1 minus the filling factor times the stray light that I gave it. So slightly different in each observation
Not exactly
set.
the filling factor either. Yeah.
Yeah.
Are those parameters, or are those recorded then in the outputs of the Merlin?
Yeah. So both the filling factor is recorded, and it's also more complicated than that. That stray light components allowed us to shift in velocity.
Okay.
So that is also recorded. So just two free parameters for that stray light factor, which is one, the amount of it, and second, the Doppler shift that is applied to that observed stray light profile to obtain a good fit. And yeah, that of course, again, it's your model now.
Right.
And the results that you get depend on your model. And I would say additionally that adding more free parameters into the model just leads you to more degeneracies typically. Your fits might be better, but your interpretation gets harder.
Right.
We can talk about it offline if you want to. Well, you feel free to ask another question.
No, I just clearly the machine learning inversions that I've done with Merlin and Hinode images just were really poor in the quiet sun, and so a lot of what you're describing, it helps explain the results that I saw. Yeah.
How do you train those neural networks?
Well,
On
it's very
synthetic
interesting.
data?
We can talk about it. No, this was just Hinode and Merlin. So level 1 and level 2 from Hinode. But this is really helpful in understanding the results.
Okay, yeah, I'm curious to talk to you more about this actually. Nancy.
My question was similar, like how you actually determine the filling factor.
Well, the filling factor,
in-
yeah, it's a it depends on the code, right? So what I introduced is technically the magnetic filling factor. So what, there's multiple ways of doing this. In Hinode, it's more treated like a stray light factor. So you give it a stray light profile and it's like, this is my non-magnetic component and it's prescribed. Other codes do, you know, they do two millennium models, let's say. One, and typically they're both identical. So you have the same thermodynamic variables, but one of them has also magnetic field. Or you could have two completely different atmospheric models, one with just the thermodynamical part but no magnetic field, and the other one with a different thermodynamical part and magnetic field. But now you're like doubling the number of free parameters of your model, and therefore, you know, again, the interpretation gets a lot harder because you have a lot of degeneracies and you're never sure you get them. Sometimes it's necessary, sometimes it's not. But you want to, I would say one advice is go with the simplest possible model that you can get away with, and don't add free parameters or don't use added free parameters if you don't need them to fit your spectra. Yeah.
So at the beginning, we talked about that we have the generacies that one same model will actually reproduce the same spectra. And then we talked about minimizing chi-square, so we can actually have like the same chi-square for the same two models. So which one results we are going to choose?
When you have the same chi-square for two models, then
Or-
you're going with your gut, man. I mean, I think it depends. When the degeneracy is intrinsic, you get two chi-squares with the same value for two different models. And I'm thinking of the azimuth ambiguity, which is the obvious one. So in the Zeeman regime, you have always two solutions for the azimuth that are 180 degrees apart, and they produce the exact identical same Stokes spectra. So they're going to produce the exact same value of chi-square, and they're two different models distinctly. You can't choose. And I'm going to say that, and then I'm going to say, and next Friday, Graham is going to tell us about magnetic field disambiguation techniques that use additional assumptions to discriminate between those two solutions. So you have two solutions, but now you put some other physical constraints on top of your problem to discriminate between those two solutions. And typically it's a constraint about continuity or about, you know, in general about your magnetic field, but I'm not going to speak to disambiguation techniques because no. Yeah. Can you get the mic, please?
At one pixel, then the direction 180 degree does not matter physically at all, right? It has no significance. But if you look at a larger area with field that connects, then that direction starts to matter.
Yeah. I mean, if you, in the penumbra of a sunspot, right? And you have one magnetic field pointing outwards and the other one pointing inwards to the penumbra. I mean, like, I mean, most likely they're actually both in the same direction. And you don't have a ton of current, you know, going on. Or not, right? Jonathan.
I guess in general, I was just wondering how computationally expensive this whole process is, because at least with like what we went over today with iteratively changing the input model parameters, reducing chi-square and optimizing that until the synthetic and observed can be improved. I guess my intuition would say like that seemed really computationally expensive for like a single inference. Then when you think back to like HMI or Hinode that has to repeat this for like millions of pixels for a magnetogram, and say we get like tens to hundreds of magnetograms a day, then that seems to, I guess, suggest that somewhere along this pipeline we've made it efficient. So I just wasn't sure, like.
Yeah, I mean, that's a fantastic question. The answer is not straightforward. The millions in approximation is as almost as fast as you can get it. Like you can invert a spectrum with, you know, hundreds of iterations. Usually you don't need that many, let's say 30, 20, in fractions of a second. So you I'm not saying that inverting HMI data on a 12-minute cadence, 16 million pixels in a 12-minute cadence is straightforward. You need big machines for that. But they do in Eddington. Let me give you the other extreme, and Roberto might cringe if I say this out loud, but Roberto and a bunch of others just developed an inversion code that takes into account non-LT, scattering polarization, Hanley effect, and whatnot. A single inversion with that code right now, as it stands, and things will improve, takes about 1,000 core hours for one pixel, as opposed to fractions of a second on my laptop for a Milne-Eddington. So they span the gamut. They span the gamut. So Milne-Eddington you can afford to do in a pipeline. Pretty much no problem, I would say, right now. Once you go to more sophisticated inversions, that problem takes longer. The forward modeling takes longer. The inversion problem, of course, therefore scales up too. And then you're looking at what Kurt is doing. You're looking at using machine learning techniques to speed up the problem by many orders of magnitude because it's just completely untractable. Sorry, it's not a straightforward answer, but it's a concern, absolutely. Michael.
Want to add a historical piece. Of you weren't in the field yet, I guess. There were all the groups that were developing trends to measure electromagnetic field observed the same sunspot configuration on the sun and together and compared the results. It was a devastating outcome. And that was one of the reasons why APO then started the development of Stokes polarimetry in various versions, deployed them, leading to the advanced Stokes polarimeter, which probably was the first really precise instrument.
And I want to add to Michael's point, it's like not only the instrument, but two inversion codes based on Milne-Eddington with the exact same physics in them will arrive at different results. Maybe just in a minor way, maybe in a not so minor way. And this, depending on how you implement the algorithms and maybe some additional extra assumptions in it, this problem is not straightforward ever. And you want to be mindful of those things and know that they exist at least. And just look at your inversion result. Again, if you go and get data from the Hinode pipeline or the HMI pipeline, look at them with a critical eye. And when you do your inversions, also be mindful of some of these things. But don't despair. I mean, I always present the worst part of the inversion process, but it's doable. You just want to make sure that you know your errors, your uncertainties, your caveats, your limitations. So, shall we go for lunch? I made David share it with everybody. So.
Can you hear me?
No.
Hello? You can hear me already?
Yeah.
Okay. So I got a question about how do you see like the profiles, the different human components in box profiles, okay? And I was explaining before, or we have seen that this when you have a triplet, you just have 3 different components, the red, the blue, and the principal component. And when you have a multiplet, you have many more components, okay? But in practice, in your profile, you just see the same Stokes V profile, okay? So there is one way, if you have a Millennium code, to tweak the test, and you can just put the Doppler width of the line close to 0, okay? So the line is narrow enough that allow you to see the different components of the Zeeman splitting, okay? So these actually, these panels here, I will play around with it, okay? You can see these stocks I, Q, U, and V, okay? These are for a magnetic field of 1,200 Gauss, I think. And this magnetic field is inclined, okay? So it's 90 degrees with respect to the line of sight. These values here are actually pretty small, so this should be 0. But you can see that the Stokes Q, you increase the Doppler width, would be the typical Stokes Q profile that you see, but you have the contribution of many Zeeman components, okay? In this case, and also in the Stokes side, you see the different components because the line has no Doppler width, okay? And you can see them, but you can play around actually. So you can, well, I can try to play around. You can, if you, I cannot see anything. So you can put the inclination to 0 and put the magnetic field vertical, okay? Okay, and you don't have Q and U anymore, but you can see that the central component in the Stokes I is missing actually because the magnetic field is vertical. So you just have a right circular and left circular polarization here. Okay, the red and blue components. And in this case, it's a multiplet. If you just go to another line that is a pure triplet, like the 50 to 50.2, okay, and you do the same, you have exactly a triplet. You only see 2 components because the magnetic field is pointing to the observer. You have the red and blue components in Stokes I and the red and the blue with different sign in Stokes V, okay? As soon as you put a Doppler broadening here, you will recover your Stokes I and your Stokes V, the typical profile you see, okay? At this, I don't. Can put the other one. Okay, and this is when you have a multiplet, you have a combination of many, okay? And when you put your Doppler width to something realistic, I cannot see. Huh? Then it should work, I hope. Ah, no, doesn't work.
A little too much.
No, because I think it's maybe too much. I was touching, I don't know. Ah, yes, because this, well. Ah, no, because, no, yeah, I know why. Sorry. I have to put this. Ah, this. Now, okay. Sorry, this is the profile that you would see in this case, okay? With a longitudinal magnetic field pointing to the observer, and then in this case, this is a multiplet, okay? And you can see this Zeeman, okay? This is the combination of 5 components. These 5 components in Stokes I, actually you had 5 components here, 5 components here, but actually you also see something in the middle. And that's it. I think. If you have any question or you want to see anything else, but this is something that you can play around if you have a Millennium code, okay?
Want to see for changing then in this.
You speak up a bit. We cannot hear.
Sorry, my question. Yeah, what would the result be if we change the inclination?
So this is not really typical profile because I don't know the parameters. I cannot see them very well here, but actually you have Q and U now.
I think you have a super high eta zero, and that's part of the reason you have that flat, saturated spectrum.
Yeah, but it's a matter of putting the right numbers and so on. It was just the purpose to see the different components.
Yeah, yeah.
Can't really see that, no? Don't have Doppler width, you would see the Doppler bordering line is much larger than the separation between components. From magnetic field.
I have a question, like when you in earlier case, you put just line of sight magnetic field. Then in the just in transition, there were 5 transition on red and 5 on blue. But when you increase the Doppler width, there comes some absorption in the middle as well.
Center.
Yes, in the center of the line. Yes. So it came just because of the Doppler.
Yeah, and I will check because I cannot see very, so I don't see very well the screen, and I don't know if the parameters are right there. So the line seems to be saturated, no, on the bottom. So probably this is something miscalculation, or because you will see the profile, the ones that we have seen in the presentation that.
Yes, yeah, that's exactly
Yes, that answers your question. No?
Thanks for that. Other questions? Anything that has come up today on the last few days? I've not been monitoring the Discord Q&A thing.
No.
If there's anything there that, okay.
Coming back to, if anyone is interested, I also have an IDL code that you give it the quantum numbers of the 3 quantum numbers of the upper and lower level, and it will plot you the splitting profile, the splitting for everything, not modified by the field and orientation and so, but just the same on splitting patterns pure.
Yeah, so I have a question, I guess, about your presentation, Rebecca. So you had talked a little bit about the nonlinear regression methods used for inversions, and how like a gradient descent like Levenberg-Marquardt can kind of lead you into a local minimum that isn't necessarily the global minimum solution. And I was wondering if there are any inversion codes that use techniques like simulated annealing to try and get around that, like where you temporarily turn off the gradient descent and to try and kick your solution out of any local minima and kind of back into the global minimum, or if they just kind of work with gradient descent and you hope for the best.
So I don't have a very good answer for you, but I can think of a couple of things. First, I'm not aware of inversion codes that use the annealing methods. I don't know, I could be missing some. I remember the original version of Hazel had sort of an algorithm before the Levenberg-Marquardt that did some sort of like parameter search, sort of coarse grid kind of situation going on to then start in a better point of the parameter space and then use a Levenberg-Marquardt to refine the solution. Typical thing that a lot of inversion codes do internally, and this you might not notice as a user, is you give it an initial guess, it kind of does its iterations, and it's like, this chi-square is crap, and then it eventually it kickstarts the inversion from a different place. So it starts either randomizes your original initial guess and puts it in a different part of the parameter space, or it does some other things. But maybe David has another answer to this. And these are things that I can think of off the top of my head. And you may not know of it because it's implemented inside the inversion code. So it's doing that for you, that sort of starting in different parts of the parameter space, but they might only just do it when it feels that chi-square is too big and it's not really converging.
Yeah, the only thing that there are some codes that use genetic algorithms.
That's another one, yeah.
Like the brutal force searching for minimums, because they really take a lot of time to search all the parameter space and so on. But I wouldn't recommend that because of you need time for just inverting a single pixel.
Merlin does this, but it does it as a initial kind of scoping of the terrain, trying to find something that is a suitable initial guess for then using a Levenberg marquardt. Then there's PCA-based inversion algorithms where they do like kind of almost like a database search of, you start with a big, large synthetic database of spectra and model atmospheres. And then you sort of decompose these synthetic spectra into principal component analysis components, and you sort of reduce them to a kind of small basis of coefficients. And then you do the same with the observations, and you try to find the best match with an existing synthetic database. Again, those types of codes don't necessarily give you a refined solution, but they could be used for an initial guess. And then refine it with a Millennium that kind of goes into the sort of more detailed, refined grid of model parameters, because it's not constrained by a grid of model parameters. Machine learning inversions don't necessarily have these issues. They have other issues, but they don't run into local minima of chi-squares. Any other thoughts?
Machine learning does, you have to do the full solution with whatever method you have decided to adopt to use, right?
Yeah.
And then you call that good. And then you tell the machine, okay, you learn from examples.
So the machine learning, and
not exactly to the point of what Jonathan was asking.
And well, it is more of a global approach, though. I mean, you have multiple ways of doing this, and Kurtz would be a better person to talk about this than me, but you can do it either on synthetic spectra or observed spectra. But what you need is, two model atmospheres and a database of spectra and a mapping, a known mapping between the two.
Mm-hmm.
And then you train an algorithm to carry out this mapping in the training set. And the algorithm is not radiative transfer constrained, it's constrained by the data that you give it. And then you have a function that maps those two things, and you give it a different observed spectrum, and it should be able to come up with a solution that more or less is somewhere in the maps, the part of the parameter space where it should be. So in that sense, it doesn't end up in these local minima, it doesn't exist. But maybe you can, why don't you come here and speak to that?
Yeah.
I'll just say one thing, and that's that empirically in other domains, in highly dimensional spaces, the local minima in one parameter is broken by a gradient in other parameters, so that the overall gradient descent algorithm that you use in machine learning can leverage information about other parameters to continue to descend, and oftentimes avoids local minima that way.
Right.
And just another kind of observation is that rather than sort of ad hoc or artistic choices of weights, there are architectural ways in neural networks to learn those weights from the data as well. So you can learn the 1, 10, 10, 100, or 100, 110 exact values from the data itself, which is kind of interesting.
Yeah, that is interesting, actually. From the typical statistics of the data set that you give it to train on, right? Yeah. And even Milis will be giving a lecture on machine learning inversions next week, so we can discuss this at length next week too.
So first, I have a comment regarding this discussion first, like, how do we even know if we are reaching the global minimum?
You don't.
So
Yeah, no, you don't.
that's my point. I mean, like, yeah, I mean, of course, if we have a good spectrum, if we repeat with another starting position, if we reach to the same, we could maybe say, okay, we are in a global minimum, but I don't think we can a priori know that.
I mean, I think as far as I know, all you know is that is my fit good or is it not good? Can I fit the spectrum with this model?
Yeah, sure.
But yeah, I mean, I don't have a better answer than that. That doesn't mean there's no degeneracies. That doesn't mean there's not a solution that's slightly better.
Yeah, I mean, I agree. I was just popping up the question, like, do we have, I don't know. So actually, I do have a question about Middle-Eddington inversion. So we discussed that you have like two lines, so we need kind of two Middle-Eddington models. But can we actually stack, let's say, Middle-Eddington models for one line so we can catch, for example, different slopes of source function? Actually, what do we gain with that, and how complicated would it be?
So Middle-Eddington, one of the approximations that you have is that your source function is a linear function, okay? But you can continue there. So you can make a Middle-Eddington. Remember, Middle-Eddington is just that the propagation matrix is constant. You can put a source function, which is a combination of exponential functions with 5 parameters, okay? And then you will have a source function that can really change optical depth in a Middle-Eddington model. You can fit lines in absorption and even in emission, okay? So you can go farther there. The only thing is that you have to be sure what that you're doing, whether your approximation is valid, okay? That's the important thing, but you can make it more complicated. You can even think about slabs models, and you can combine several slab models. Okay.
Meaning for each slab you define like Middle-Eddington model.
Yeah, you can combine two different slabs. It is something typically done for the helium-1030 line. When you go to a prominence or somewhere else, you know that you have two different structures in your line of sight because you see two different components, and you know that they are coexisting in the same pixel. So you can just put two different slabs and then have two different models for explaining one single observation, okay?
Yeah.
And that could be valid, actually. But again, you have to be sure that your approximation is valid, okay? In the case of so we don't have infinite time, no? But in the helium-1030, this is a good example because you can, some profiles that have two components, you can fit them with two different layers or two Middle-Eddington layers, okay? But if the illumination from the bottom layers is too high, okay, then you are introducing some other radiative transfer effects in the helium line, okay? So, and you can see that even though you use two layers, you cannot fit the profiles because you have some other transfer effects, okay? I don't know I don't know if they will show next week Hazel fits, but there is one of the examples that I think I sent you to you, no, Jana?
Yep.
One of the examples actually is that one. There is a profile that sees has transfer effects because it's illuminated from below. And even though you put the two layers, you cannot fit it, okay? And it's very interesting because in that case, your assumption is just not valid. Okay. Actually, in that example, we don't know how to fix it anyway.
You would not say?
We don't know how to fit it.
You don't know how to fit it.
Okay, because it's something else going on. But yeah, you can combine many things. We tell
which one
is it, so you can try to fit it next week, and you will see you cannot fit it. Okay, so
Fitting the normal ones was already a bit of a so even an eye would get very different results all the time. So.
yeah, it's tricky. It's tricky. Yeah. And there is another one, which is, I don't know if you have that one. It's a prominence that goes from disk to limb. Okay.
Oh.
And you have illumination coming from the limb into the disk side of the prominence.
Oh.
So the profile is really strange. And you know, it's a combination of two things, but you don't know how to fix it, how to fit with two different models, because it doesn't follow that simple assumptions. Okay. So there is something else going on. And it's basically transfer, no, in the helium line.
So I have a question. I mean, thinking about this combination of different profiles, because there are multiple effects at work. Going to higher resolution, like the thing you showed today, the HMI with the DIC is the thing. In a sense, shouldn't it make things easier? You know, shouldn't you be able to see the pure effect of the effect of a pure magnetic field or a filling factor of 1 and whatnot? Take a perfect treatment like the 50 to 50 or so.
I mean, that just made me think of a paper by Andreas Lagos, like from Sunrise. We resolved the flux tube for the first time ever. And then I look at Matthias's simulations, I'm not sure he's in the room, and I just want to cry. Because if that is the reality of it, it's not just about spatially resolving the horizontal domain, but the vertical domain, you can't resolve spatially, right? Because you have the photon mean free path, which is whatever, 100 kilometers. And in that integration along the line of sight, you're never going to resolve. And if the fine structure is such that
you're saying the gradients of velocity,
if they change really fast,
so it changes very fast.
I mean, I'm not going to say never. There's, you know, again, the tool of using multiple lines to do your spectral line inversions. Yes, to your question, high spatial resolution should help mitigate a lot of these issues.
Or maybe not. Maybe it introduces those other ones that you.
Well,
in a
I
sense,
mean,
you
those
wash
are, no,
out.
those are there anyway. But you get weirder profiles, I guess.
Right. And
You get spectra that are less and less symmetric, the more resolved they are, I would say.
because you feel all the gradients essentially.
And then you can't use a middle Edmonton anymore. You're like, nothing is symmetric ever.
Yeah.
I don't know, you tell me, you've used Deacon's data.
Yeah,
Yes,
we did. So how did it go?
No, it looks pretty good.
Maybe the resolution is not as
Oh,
high.
It was good.
Maybe there is hope.
Yeah, I think so. Good.
When I think of these things, I always remember something that Alfred once told me. He says, misfortune is conserved. So increase the spatial resolution, you're going to find other issues. And then in that context, you're always photon starved because, yeah, so you're always going to run into noise. You're always going to run into those other things. You can't just indefinitely increase your spatial, spectral, and resolutions and sensitivities. It doesn't work that way.
No, only the number of photons is conserved at the diffraction limit. No. Photons per unit time.
Yeah, well, you need it. It's always a trade-off, always.
I have more the question is like a curiosity. What is the region of the FAL model and the HSAR models? How, I mean, it's historical reasons, but how can the people realize that it is a good model or not? Or what's the process? You know?
So they're kind of they're actually inversions because they were made to fit many observed profiles. In many cases, averaged over a very large region, so average spectra, but they were inversions by hand, like changing the temperature and then self-consistently solve many things, the radiation transfer, the ionization, etc., because they would combine the radiative transfer in many different atomic models. and make sure that all is consistent, but they were not automatic inversions. They were actually inversions by Gene Averett would sit there at his desk, tell his programmer Rudy Leuser to change the temperature here, and then see what the effect was, and so adjust the temperature structure that way. So yeah, they were self-consistent physical models that try to fit as many spectral features as possible.
Sorry, a question, weren't they built from continua measurements mostly?
No, not only. No, like calcium H&K lines were important. UV lines were important.
Because there's a feedback. In those models. Okay. I have a anecdote about that. About I know when 15 years ago. 15 years ago, and I don't remember. I remember one of the actors. I don't remember the other one. The other one was saying, "Oh, we do inversions, blah 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 blah," and the other one was Weir, who was this famous older German sort of physicist, and he goes, "Well, those aren't semi-empirical models." And the young one was like, "No, these are inversions. No, those are semi-empirical models. You just let the computer do it for you instead of doing it by hand." That's what it is. They were called semi-empirical models, but it's the same thing. It's just now you do it a lot of time, very fast, and then you would have Leuser to change the temperature and see what happened.
It is slightly different. The semi-empirical is more because they use much more physics than we use in a forward modeling of a typical inversion.
Oh yeah, okay.
Right, because we don't always determine electron density, although that some part is sometimes part of it. But the Val models, and so the target was really to determine every property of the atmosphere, the full physics.
Sure. Here, if you use like Milne-Eddington, you just determine these three parameters, like the magnetic field, the velocity, the slope, and so on. But you know nothing about the pressure of the electron density or anything.
Yeah, so that's one of the limitations of Milne. That's one of the limitations of Milne-Eddington is that you don't map to thermodynamical quantities. You map to line fitting parameters. But I would say that in terms of the magnetic field treatment and the line of sight velocity treatment are so physically consistent. It's the thermodynamical part that is mostly a line fitting exercise with that bears little resemblance to thermodynamic quantities. Although you can do what Hans said, you can take the source function and then make an assumption that is the Planck function. And if you believe there's no degeneracy in the inversion problem, maybe you can actually get a temperature. But yeah, it's not based on thermodynamic reality. And I like the semi-empirical. I mean, it's semi-empirical. It's a model because it's a forward model in each inversion code. It's not as sophisticated as the FAL models and so on. And it's empirical in that you take data, you're trying to fit an observation. So in that sense, you're reconstructing the model atmosphere of the sun with observations and model at the same time. So what you get.
Yeah, I think basically there's no difference between what we traditionally call these semi-empirical models and inversions. Is just degrees of sophistication in different parts.
And the fact that FAL models are like average models of the atmosphere and that you fitted average spectral profiles, right? So no single observation from Hinode you're going to be able to fit with a FAL model. I mean, there's going to be, you can start with an initial FAL model and yeah, let the inversion code tweak it to be like, this is a better temperature stratification to fit this spectrum. Yeah. There's no more questions. We should let Kevin come to the stage.
Okay. Well, this will be the sort of the final lecture here on our observations, the instruments and techniques. And this is my favorite part. It's the gloom and doom part about, we've been looking at these idealized, these ideal polarizers and retarders and the observations and how they all fit nice and neatly into these Euler matrices. But now we're going to start to see some of the actual, challenges when we're actually observing the sun with sort of real instruments through a real atmosphere. Called it observational realities, right? So one thing, if you ever, talk to people doing polarimetry, they'll, often it'll devolve into a debate about precision and accuracy and which one people are, trying to achieve. The 10 to the -5, is that a precision? Is that an accuracy? And you've probably all seen, the difference here between something being, not accurate, not precise, here very precise. They're shooting at the target and they get a lot all in the same place. Every time, they shot, every time they recorded, measurement, it was very similar, but it wasn't in the right place. Or, the observations, or they're shooting here, throwing their darts, all were clustered around the right place, but rarely got, in the bullseye. So, that is accurate, but it's not precise. And then, the goal is to, of course, both be accurate and precise. So, have the observations be repeatable. The darts are always hitting close to the same place and they're near the bullseye. I think there are a couple other options here that we have to also consider, right? Beyond these four, there's one that the data is so noisy, I can't really tell whether it's accurate. It's so imprecise that it's hard to know, right? Are these, is the average here near the bullseye, or, is it somewhere else? And then there's, the option that we really face when we're doing these kind of observations. I don't know what the bullseye is. I get a lot of measurements and they're sort of clustered, but I don't have, no one's telling me what the center of the target is. No one's telling me what the bullseye is. And so it's hard to know if these are accurate or not. But we're doing spectropolarimetry. We're not playing darts. So what does this mean when we talk about spectra, right? So here are two examples of sort of a Stokes V kind of spectra, where I have some observations here, and I've added some noise to show, these are accurate. They're sort of following this ground truth, the red line, right? But there's a lot of jitter in all these measurements, around the true value. So, it's accurate, but it's not too precise. Or the other option is, I have an improved signal to noise over here, right? The values are all clustered closer to some, nominal value, but this isn't accurate, right? My spectrum here that I'm reconstructing doesn't match the ground truth. So something's gone on in the recording process, right? And I'm not getting out the expected, Stokes V profile. So this is what we would, say would be a precise, but an inaccurate Stokes V spectrum. And here, if I could improve my signal to noise, I can get, both accurate and precise, which is obviously better than being not accurate. Now, there are a lot of points here. This was taken from the FTS Atlas, which has a 2 milliangstrom sampling, just to show you, what, even with the spectrograph, what we're typically recording is a lot fewer points, right? This is now with a 20 milliangstrom spacing, and you see that already here, it's harder to tell whether this is accurate or not, right? Is this, I only have a few points here in the wing. Am I properly reconstructing this spectrum, or is it off? So this is that case where from a single spectrum, I can't be sure whether I have achieved accuracy or even how precise it is. So can anyone, just wondering, if you're looking at these spectra, what is the sort of precision we're getting here? Is it 10 to the -3? 10 to the minus 4. Anybody have any guesses? Let's see if this is clicking. So this is about a 10 to the minus 2 precision in my measurement. So about a 1% error in this thing. And this is with, fairly strong Stokes V component here. So about 10%. Obviously, Stokes Q and U are often weaker in these linear polarization signals, and then as you go up into the chromosphere and into the corona, the signals get even smaller. So, this is a, very good case over here. It's 3 times 10 to the minus 3. So you see what a significant change here. I've increased my signal to noise by a factor of 3, or my noise to signal ratio has decreased by a factor of 3. And you see that makes a significant difference in the amount of jitter in my measurements. So, it seems like it's not a big deal to make that, factor of 3 change, but it is, you can see the effect on the spectrum. Going back to this one, so this is this very noisy spectrum, and that one is now 3 times 10 to the minus 2. So this is a factor of 10 difference in my noise to signal ratio. So, that's a factor of 10 is a significant change in the quality of the spectrum. So just, when you're thinking about these, oh, I just need 10 to the minus 4, right? I mean, that would be, you'd almost perfectly reconstruct the spectrum at this, with this significant Stokes V signal. So what does that mean now, in actual spectra? Let's look at some spectra with some different noise characteristics. And here are 3 Hinode spectra taken with slightly different exposure times. And Bruce Lights again has, summed these up or combined these. So here it is with 4.8 seconds. And sort of the signal to noise here is about 10 to the minus 3, or the noise, level, is 10 to the minus 3. So you can see the Stokes V signals pretty well, or, some of them. But Q and U seem to be buried down there in the noise. You don't really see them. If I double my exposure time, don't see too much of a difference, right? Can start to glimpse a few Stokes Q and U signals there. But now if I increase it by, almost a factor of 8 here, now I really start to see that there's a lot of Q and U signal there that was buried in the noise in these two. And over here in the V, I start to see the Stokes V all along the slit right here. With these lower signal to noises, there were gaps where, well, there's no Stokes V there. Well, it turns out there is. These were all sort of scaled to plus or minus 0.003, so about 3 sigma of these original measurements. But now I've improved the signal to noise here by this factor of what was that, about 5. So I can change the scaling here now. So I'm scaling again close to plus or minus 3 sigma for these data. And now you see all the Stokes V pretty much, all along the slit, in almost, most places there's some kind of Stokes V signal, and you can really start to see a lot of different Stokes Q and U signals there as well. So, this is the effect of increasing signal to noise, just, by beating down that photon shot noise. So what do we have to do to, get to, what is entailed in getting this better signal to noise? Well, I just need to add up more signal, right? In at least as far as, the number of photons is involved. So my signal to noise ratio just goes as the square root of the number of photons. So, once I calculate my photon flux, I can sort of figure out what my signal to noise should be. But there are a couple things to note. The maximum polarization, the maximum efficiency you get in any of your Stokes Q, U, and V measurements is that square root of 3, right? If, in a balanced modulation scheme, the number of photons that of Q, U, and V is just a square root of 3 of the total signal. So if I'm, calculating my total signal, I need to say, well, in any of those Stokes states, I'm really getting less photons. And then a lot of what we saw yesterday, a lot of it's differential photometry where I'm taking I plus or minus Q and subtracting those off. So I often, adds additional noise into a single measurement. So I, really need to have about, 2 times the photon flux to get a good signal to noise in my Stokes, my 3 Stokes Q, U, and V polarization states. So for a signal noise of 1,000, right? If I want 10 to the minus 3, which is, a good signal noise, especially, sort of the minimum for maybe chromospheric measurements, I need to acquire about, 2 million photons. And that's, for a typical camera, I can't acquire 2 million photons in a single exposure. There's a limit to how many electrons can be captured in each little pixel of silicon. And so, typically photons in a single image at most are 50,000. Oftentimes there'll be less, but let's say you can get 50,000 photons in an integration. Well, now you have to think you have to combine 40 images to get that kind of signal to noise. And if I say, well, I just want 10 to the minus 4, what's that going to take? Well, now I need 200 million photons, right? I have to go up by a factor of 100. And now I'm combining about 4,000 images in order to get that total number of photons in each pixel. So, it's just one thing to consider about how many, images often go into one of these, single exposures. Even in this, here is a combination of multiple images. It wasn't a single 67-second exposure. And we'll see, how we figure out how long we need to integrate. And that depends on, that integration time. Now, if you say, okay, I have a target integration time, I know my photon flux, someone, sort of provides that from the instrument, in a certain resolution, you have a photon flux. And there's also this problem, and that'll sort of tell you, well, I want a 67-second exposure, for example, or a 9-second. But the sun is also evolving on those same timescales. And so the evolution, speed, how fast the sun is evolving, whether that's changing, in different ways, but things often move in the field of view, or, on the sun, things are evolving horizontally, they're evolving vertically as well, within our pixel, things are always changing. And so, we can sort of say, given the sound speed or how fast these things are moving, I can sort of set an upper limit on, how long I can integrate before this thing in my pixel, right? This is the size of my pixel in kilometers on the sun. And if things are changing at some speed, then I sort of can calculate what's my target time. I need to acquire my information before things evolve in that pixel. So for example, this could be, 50 kilometers on the sun, and sound speeds are typically 7 kilometers a second. And so you can say, well, I have about, 7 or 14 seconds that I need to acquire, all my information before. Now I get confused by the evolution going on underneath, during my acquisition. And then the time scale then to get a certain signal to noise goes as my resolution element squared, both, the size of that resolution element on both sides. And, there's sort of an optimum place here where I can sort of get a best resolution and acquire everything within that evolutionary time scale. So another way to, to think about this is as a big trade space, right? I have to, I have a series of observations I want, but I have to make, there's always decisions to be made. We can't acquire everything all the time. So, we've been talking about sampling in time, right? I can change how long I integrate. That's one way. Important here in instruments is to optimize the efficiency. So you're always acquiring photons as much as possible and not spending a lot of time moving optics or changing things, because then you're leaving photons fall on the floor, and that's just wasting photons. And the other thing we often do is change our sampling in space, so that the spatial resolution, how big that delta X is. So with the slit spectrograph, one key way to do that is you can often change the slit width, make your slit bigger, and that will allow more photons to get into your spectrograph. Of course, you lose spatial resolution when you do that, so there's a trade-off there. You can also change how densely you sample, as we were talking yesterday about scanning. You scan the slit, but you have choices on how densely you scan that slit. And this is an example of sort of an original underlying image here. And now, assuming I have a 0.11 arc second slit, I can move that slit very densely across my image. And if seeing is perfect, I would get a nice image that sort of mostly recovers the original resolution. There is a smearing because of the width of the slit, but I recover most of that. But I could move the slit more sparsely. I could move it, instead of moving it 0.055 arc seconds, I move it in adjacent steps 0.11, and here it's 0.22, and now I'm smearing things. So I have a trade-off. I can move more quickly across my scene and sample this whole region in a shorter time, but at the cost of spatial resolution. And then the other big one is this spatial binning. We can just combine images in our image plane, whether that's with a slit or an imaging spectrometer. We lose spatial resolution just by summing up in the spatial dimension. And then there's the option to change our sampling and wavelength. Spectral resolution is often, baked into the instrument in the design phase. It's part of the, fundamental aspect of the grading or of the Fabry-Perot spacing or so on. So that's kind of not often, can't be adjusted, but I could bin my data afterwards, especially with the spectrograph, where we said you have a lot of spectral samples that you've recorded across this detector. You could bin those spectrally afterwards to try to improve your signal to noise. And you could also choose how many samples you want to take with a tuning imaging spectrometer, where you're tuning to different wavelengths. You can get more or less images, and that folds into the amount of time it takes to scan through a line. So there's all these complicated choices to be made. In terms of spectral resolution, right? If I reduce my spectral resolution, and here's an example of what happens, I just start to lose information on the line profile. And, here I lose this signal of the magneto-optical effect if I, smear out by 100 milliangstroms. And so, just when you're going to do this inversion process, the less you're losing information, or you're smearing it out, and it's, it's less, it'll constrain your output atmospheres less if I have a more smeared profile. So, that's a trade-off. So, a way to think about this is this sort of part of this trade space is, a graph like this, where I have my spatial sampling down here and an integration time up here. And, these are connected. As my spatial sampling gets smaller, we saw that the amount of time I can integrate also gets smaller, right? So as my, get smaller and smaller pixels, that amount of time decreases. And here's sort of the minimum noise to signal ratio over here. So that, that 10 to the minus 3, 10 to the minus 4. And these are sort of plots for different aperture telescopes and different wavelengths. But, we look at the dotted line here. For example, for a 4-meter telescope like DKIST, you can sort of see as you go to smaller pixel sizes, smaller spatial sampling, you end up, the amount of time you can integrate gets smaller, and the maximum achievable signal to noise goes down. There are assumptions baked into here about that velocity and, the resolution and the overall throughput of the telescope, but the trend lines remain the same. So, if I say, well, I want 10 to the minus 3, I can draw a line across here and see how that sort of falls for 2 different telescopes at 500 nanometers. And that says for, DKIST, I need about, I can integrate for most 4 seconds, right? Integrate for 4 seconds at 0.0 4.05 arc seconds resolution, and I get 10 to the minus 3. Whereas I can, integrate for 7 seconds with my 1.5 meter telescope, but only if I, accept a lower spatial resolution in the end. So it's, just part of this whole sort of, all these things are intimately tied together, the resolution, the sampling, the sun evolving, and it makes it, it requires sort of a lot of decisions about, which are the key parameters that one wants to target in an observation. Is it, high, having a high precision and a high spatial resolution, and those things often don't go together or have a, are pushing and pulling against each other. So, this sort of signal to noise question is tied up in this polarimetric precision, right? That's what we're talking about. How do we get in our Stokes IQ, U, and V measurement, how do we get, these our errors as small as possible due to photon shot noise, right? Those are just, direct results of the amount of, photons we collect. But that's not all of, the source of our errors in our measurement, right? If, we don't just have photometric error, we also have, some other problems. For example, 2 days ago, we talked about the, the Brewster angle, or this effect that different polarizations are reflected differently off of a mirror, depending on the angle of incidence, right? You have the this, Brewster angle, and this is for, a silver mirror, so it's a little bit different here in terms of what the angle is. But you see that, some polarizations are reflected differently. You also, get an effect. There's a slightly different dye attenuation here for mirrors, whether aluminum or silver. But you see, depending on the angle of incidence, I get a different dye attenuation. I can get a different retardance off the mirror. So, and telescopes often have mirrors, right? And so I don't just have an optical system where I have a retarder and a linear polarizer, and I have that perfect Euler matrix. I have a much more complex instrument, optical system. And so, the other big part of that we have to deal with is the not just the photometric precision, but our polarimetric accuracy, or at least our polarimetric precision as well. And that this all, is going to depend on calibration, our ability to understand what our instrument is doing. So here's this Mueller matrix again, broken out as all these different terms that it's encoding. So here are these crosstalk terms, the I to the Q, U, and V, that are, often problematic because I is often so much bigger than Q, U, and V. So even a small value here can be an issue. We have the, these terms here on the diagonal, which are, we want to preserve our signal through the system. Those are important. And then, there. Yeah, these are the other crosstalk terms between the other different polarization states. So the, Q to U, V to Q, and down here. So these other diagonal terms are important as well. And we'll see how to fold those in here. So, what we saw was this, we can define Mueller matrices. And what's great is you can multiply them all together, right? And each optical element may have its own Mueller matrix, but then we can sort of, those will combine algebraically, and we can have, just think of one big Mueller matrix for our optical system. And so, this is sort of the way we think about it is we have, the light coming from the sun, right? I, Q, U, and V from the sun, the true values. And then it goes through and, through this big Mueller matrix for the whole system, and we get our observations out. And so, this matrix here is called the instrument response matrix, right? And then we can invert that and apply that to our observations, and we can get the I sun out and know what the input Stokes signal was. So, all we need to do is figure out what this instrument response matrix is. One way how well do we have to know what that instrument response matrix is the other question, right? So there's a way to think about that, what the tolerances are, just by thinking of, we have the true response matrix, and then we have the response matrix we would actually, measure or deduce or calculate for our instrument. And, what we, so now in this case, we have the input Stokes from the sun, and it goes through the true matrix and the measured matrix. And then this is the identity matrix here. And it gives us the delta I, what our errors are in our measurement, right? Now our photometric errors, we can also, characterize those and know what our photometric errors are, just in the case of a specific observation, what sort of errors are acceptable. And we just want to make sure that our calibration errors are less than our photometric errors, in a specific observation or use case. And so we can sort of define what error, the error that we get out between these two, the measured and the true instrument response matrix. And that sort of tells us this delta X, which is the tolerance matrix. And, we can sort of think about what those tolerances are. What's the maximum sort of error I can have in any one of these terms in my instrument response matrix. And this is, I want the crosstalk terms to be less than my photometric error, right? That's what's, it's saying here. So, as long as these don't exceed my photometric error, I'm not adding a lot of noise into my measurement. I have these terms on the diagonal, which are sort of the allowable errors in the actual QU and V measurements. How precise does the QU and V have to be in sort of absolute terms? And a few percent in the QU and V is probably fine generally. And then I can, for these other off diagonal terms here, we can sort of guess what, for a specific observation, what is the sort of maximum value of the polarization that I expect in QU and V, right? Is it 50%? Is it 1%, right? If it's a small value, it's not going to, even if there's crosstalk, it's not going to propagate into the other terms. So, the common one is for photospheric, the Zeeman effects, right? You might have a 15% maximum polarization in Q and U, maybe 20% in V. And then as you go up and start looking chromospheric or Hanley effects, those drop significantly. Scattering polarization, it's just a few times 10 to the minus 3. And so then I can take the ratio between, what my acceptable error is here in my signal to noise, my photometric error, divide that by sort of the maximum polarization I expect, and sort of tells me, which terms are important for a specific kind of usage. And this is, gives me my response matrix that I can compare, and I know how well I have to calibrate my instrument in the end. Oftentimes we just calibrate it as well as we can and hope it's good enough. Often also because, as we'll see, these calibrations are not done for a specific observation usually. They're somewhat complex, and so you just try to calibrate as well as possible so you enable as many science usages as possible. So, how do we calibrate these things and get this instrument response matrix? We're going to start with a simple example, Hinode, the SOT, Solar Optical Telescope on Hinode. It has a nice big mirror here, 0.5 meter diameter mirror, and then the light goes down, and it has goes into the spectrograph down here. And as is often done, that polarization modulation unit, that whether it's this rotating retarder and the linear polarizer, is put as far up in the beam as possible, right? And so right out here after the exit of the telescope, you have that polarization modulation unit. And so now I want to know, well, if I put in, how is this whole optical system, right? The other thing that often happens, you have 45-degree fold mirrors, right? I want to squeeze this telescope down into a small package so I can launch it into space. There's 45-degree fold mirrors. as we saw in those plots before, 45 degrees is, you're starting to get up to those angles where you have a very significant amount of polarization that you induce into the light, right? And so, 45-degree fold mirrors are going to, have a significant crosstalk into linear polarization. So, that's important to calibrate this. So for something like this, what they did with Hinode was they just put a large polarizer, right? Linear polarizer in front of the aperture of the telescope, and then rotated it at 4 different angles. They also had a large circular polarizer. And they did the same thing, both at left and right circular polarization. And they did this 4 angles for all 3 of those elements, the linear polarizer and the right and left circular polarizers. And then you measure that output signal, right? And then you can go through and deduce these, 15 values you want to get out. You have 12 measurements here, and then you got, for each one of these measurements, you got a value of Q, U, and V. So you have 36 measurements, and you need to deduce these 15, output values. So the system is, well constrained, and you just use a least squares fitting, and you can sort of get the value for these different parameters. And what you end up with is your Mueller matrices, or the instrument response matrix. I just note that it looks like a Mueller matrix. It doesn't actually have to be a Mueller matrix, because there are other things in the system that may not be, pure optical elements, such as detectors, right? There may be a response on the detector and so on that, they don't follow the requirements of a pure Mueller matrix, but they're very similar. And so here are these cross terms, and you see I get, on the diagonal, there's the good response, and the crosstalk here from I to Q and U is very low. One value that's high here is the Q to I, and that's just an inherent effect of a rotating quarter wave plate modulation scheme. It has a large, there's a large Q component that's induced, but that can be measured, calibrated out. Now that all looks nice and simple. I mean, you can also look at this spatially and look at the value of these Mueller matrix values at each point in your field of view, right? In both this left and the right beam. And you see there's a lot of spatial variation in this. So it's more complex than 2 simple matrices. You have to consider that there's spatial variations of these Mueller matrices at each pixel in the field of view. So, one of the, realities is it, not every pixel responds, identically. So this, as I said, was a very simple case. That telescope here, is on a spacecraft. It always just points at the sun. The instrument here is, again, as it's a spacecraft, is bolted to the telescope, always in the same orientation. It's never changing. So this is a nice, simple case. I have a question. Yeah. 2 questions.
The Mueller matrix measured one that you showed is at the end of everything. This is a
yes.
spectrum there was a spectrum taken.
Right.
Could you comment why you say the modulation is just as close to the telescope as possible?
Up here?
The modulator unit, yes.
This here.
Yeah.
Right. The point of doing that is it's before these fold mirrors. So the idea is to put that modulation, once I've gone through this modulation unit, I just have 2 polarization states, right? That's what comes out of that combination of the retarder and the linear polarizer. I just have 2 orthogonal polarization states. So it's a simpler set of polarization that's going through my telescope now. And so I'm not getting crosstalk from, the circular to linear polarization, as it reflects off these additional optics. So it's a little simpler, or there's less calibration that's involved. The calibration has to be, is easier to do if I get this up here and set up those, convert my incoming Stokes Q, U, and V to that, the two polarization states. Was that both questions? Yeah. Yeah.
What's the differences between left and right? Why do you measure both?
Why do they have these two left and right? We mentioned that yesterday. We'll get back to it and to understand, why you want to do that. But this is, they're the two polarization states that come off, through my modulator. Right, I have the Q and the U, the two orthogonal states. And if I use a polarizing beam splitter, one is I plus Q and one is I minus U. If I use a polarizing beam splitter, I measure both of those at the same time in a left and a right beam, as they're called. And, in this case, that's just for efficiency. I get both sets of photons in my, in my actual readout. And then there's other signal to noise issues that do that too. But yeah, it's just getting both the I plus and I minus output from the modulator. So, then things, start to get complicated now when we're observing from the ground. So, as you know, during the day, the sun moves in the sky, right? So we want our telescope to follow that motion. And so a lot of solar telescopes, they used to be up on, you wanted to get that aperture as high up above the ground as possible, because the seeing, you'd get less ground heating and seeing from the ground. So you put your telescope way up high, but you wanted to have it, you didn't want to put a big, large telescope, up perched on the top of your tower. So you would just sort of pick off the light and send it down to the ground to be, to your instruments. So, a common way, they used heliostats and coelostats at Mount Wilson, for example. And, with the Dunn Solar Telescope and telescopes in the Canaries, they use what's called a turret, where I just have two 45-degree fold mirrors. And, I can rotate one in azimuth and one in elevation and always track the sun and see it all the time. And I just said two 45-degree fold mirrors right at the start of the telescope. That's bad. The other point is that they're two 45-degree fold mirrors, but they're changing in time. Their relative angles are changing as this thing is tracking the sun during the day. One is rotating in azimuth, the other one's rotating in the opposite direction or the opposite plane. And so, the angle between these two is changing. But still here, you can go up to the top of the telescope, put a big polarizer in front and try to calibrate this whole optical system, just like they did with Inode. So here's 45 degrees, you get, all kinds of increases in your retardance and dye attenuation and so on. So when they built these telescopes, they weren't thinking so much about precision polarimetry. So that's why they did it like that at the time. So let's see here. This is now an optical scheme of sort of the Dunn Solar Telescope, where I have my elevation and azimuth mirrors here. And then the vertical beam goes down and is sent off again through what you see is a lot of optics at all kinds of different angles. What's important to remember, so is these things are the angle between the telescope and all these optics down here is changing in time, right? And so during the day, these things change. So that means that my whole, if I did my whole instrument response matrix, it would be time dependent, right? And so I would have to, have a different, instrument response matrix is X for every time. What turns out to be easier to do is to say, well, I'll just treat these things up here that are moving and changing during the day as one matrix, time varying matrix, and then I'll have my instrument response matrix that sort of captures all these non-moving optics that are, still complicated with fold mirrors, but at least they're not, the angles relative to one another are not changing during the day. And so, I put some calibration optics down here at the exit of my telescope where things have a fixed orientation. Everything downstream is fixed, and I can measure the X matrix by doing the same thing, doing different polarization, linear retarder and linear polarizer combinations, measure the X matrix, and then I could put that big, piece of polarizer up in front of the telescope occasionally and measure the instrument or the telescope response matrix. And I can combine those two together to get my a time-dependent sort of Mueller matrix. And so this is, it's a 4x4 grid, must be a Mueller matrix. We'll see a lot of these. So these are, this is now the different values here, can't really see them, but this is the time of the day now. At the bottom, the x-axis here is the time of the day. And so as your telescope, during the day, all these crosstalk terms here are changing in complicated ways, right? And so you have to sort of, for any given observation at any given time, you have to sort of derive a Mueller matrix, based on that specific observation. So yeah, this gets a little bit, trickier to deal with. This, what I was showing was basically for one wavelength. Of course, all these terms like the retardance, the diattenuation, they're not, constant with wavelength. Here's an example from some DKIST codings where from 400 to 1600 nanometers, you can see that these terms are changing. And so obviously, the Mueller matrices, that instrument response matrix is going to, vary with wavelength. So another complication there. And this is just to show sort of, now we looking again, instrument response matrix at a specific time, but this is the wavelength dependence, right? And so you see some of these, some of the terms are fairly constant. They don't depend on diattenuation, but some of them, do so some variation depending on the wavelength. So, just to show you all the different axes of these Mueller matrices now, right? They have a time, they have a wavelength axis, basically, that all has to be sort of taken into consideration. So, okay, before we put a big polarizer in front of our telescope, how big of a polarizer can we make? So this is DKIST, and it's got a 4-meter aperture, and yeah, no one's making 4-meter diameter polarizers, and they probably wouldn't let you hang something in front of the mirror anyway. So we have to think of a different way to do that, to take these, to calibrate a large aperture telescope like DKIST. I just point out here, this is the, primary mirror on DKIST, it's 4-meter mirror. This is actually the reflection here off of the heat stop on an earlier iteration of the heat stop. You see this big bright reflection there off the back going onto the dome. What I always find notable, I like to point out in this picture is, if you look at this, you can't really tell that this mirror is illuminated, right? Normally, when you look at a mirror in the sunlight, you can see all sort of specular reflections coming off the mirror. If you look at this, you don't see any sort of scattering, and that's just, indicates how finely polished the mirror is, so it can do these coronal observations as well. But you put a mirror in the sunlight, and almost all the light is being reflected up, where it's supposed to go. So, how do we, calibrate a big telescope like this? And, people at DKIST and Dave Harrington and Stacy Soroka have been working on this, and Amanda White, trying to, do a whole calibration. And again, with DKIST, we're trying to reach these 10 to the -4, 10 to the -5 polarization accuracies or precision. And so, we need to be able to do this pretty well. Again, we have sort of a complex optical system. Here's the sort of cartoon version over here, with light going in the telescope and bouncing and going down to all the instruments down on this Coudet table. And here we have our telescope, the light's coming in and hitting the primary and the secondary mirror. Those are nice. They're always at a fixed orientation with respect to the sun. The telescope tracks the sun, but those two mirrors, are always at a fixed orientation with respect to each other. And then there's some calibration optics that can go in here at this Gregorian focus, right here. And then we have, this whole train of fold mirrors that will all have their own sort of polarization effects. And there's a few rotations that go in here, right? These optics sort of have a constant relationship orientation with respect to each other, but then you again rotate in elevation and azimuth as you go down to the Coudet table. And so, you have some changing orientation. So there is some time dependence in the overall instrument response matrix that we have to take into account. And every coating, along all these mirrors is actually special and is all, they're all tuned and have to be measured and calibrated, but they all have the same effect, that the reflectivity is different between the two different orthogonal polarization states. And, depending on the orientation, 10, 45, and 60 in these different colors, there's all sorts of variations, both in, this, how much is reflected, basically a diattenuation between the different polarization states and in the retardants that they induce. Right? And it can be significant here, right? This is, nominally here, it's 180, but, some wavelengths, these coatings can induce a significant retardance in one of the circular polarization states. So, it's a little more complicated, but again, it's just combining up a series of Mueller matrices, right? You can treat the primary and secondary, M1 and M2 as a single matrix, M3 and M4, which are down here, where possible, these things can be combined. And then where there's a rotation here because of elevation or azimuth, you have to induce this, put in a rotation matrix, and you can calibrate, calculate all this out, and you get a very precise calibration of the sort of instrument response or the whole system response to the different polarization states. Now, as part of their work, they, can sort of make different visualizations of this. So, again, 4x4 Mueller matrix. And in this case, they're plotting the Mueller matrices now as a function of azimuth in this direction, elevation here. And so as the, telescope points, changes its pointing, and the sun rises, goes up in this to higher elevations and back down, you see these different trends. So again, it's very time dependent response that has to be all folded into the calibration process. And they, started looking closely at these things and, instead of just saying, well, what is the retardance of this retarder, right? Or what is, how much, is it changing? Or, instead of treating that retarder as having a single retardance, they can actually spatially map out what the retardance is over the entire surface of this, of the different optical elements. And so you see the retardance changes by, plus or minus 3 degrees here across the surface. And the fast axis over here is also changing by, about a degree across these optical elements. They're not uniform. And so, again, to get to the very high precision polarimetry, you have to take all these things into account. Also because the calibration at different times may illuminate different parts of these retarders. So it gets, complicated to take all this into account. But it's, certainly possible. So what are the takeaway messages? Polarization calibration, getting these X and T matrices can be tricky. Overall, solar physics, has had a lot of work in doing this. We started out with these crazy turret mirrors, trying to calibrate those in time. So, we've gotten pretty good at it. By, deeply understanding the coding properties and so on, these things become very amenable to modeling, and we can sort of calculate the series of Mueller matrices that should allow us to have a good calibration. But we always have to be worry that errors are going to pop in, and we need to understand how well we're actually modeling this thing, right? We don't know sometimes where that bullseye is, and so we have to keep checking and make sure we've got this right. So we take a quick break here, give people time to stretch, and then we'll come back and look at some other effects. I think that was, yeah. Come back in 10 minutes or something. Is that enough? Oh, question? Or are there any questions in this part, in the calibration part?
And the Mueller methods.
Right.
Azimuth.
Mm-hmm.
What's the amplitude of those black and white?
That's a good question. I don't remember. Right, this one. Yeah, I don't know what the absolute values are on these. Some of them can be. Mm-hmm. Right. I have to look in Dave's paper, but yeah. Yeah, I mean, there's a, I cited these as Harrington et al. 2017 to 22 because there's about a dozen papers where Dave and Stacy and Amanda have gone through and done calibrations upon calibrations, and they really, there's a lot of details on, all the different effects in there. And that's where that, plot is from, and I'm sure they have the values in there, but yeah. Mm-hmm.
One tricky question, okay? So I guess every instrument has its own calibration optics, probably, or I don't know.
Its own what?
The calibration optics. Do you have a calibration optics in the QD lab down?
Oh, for DKIST?
For DKIST, yeah.
I think they have, each one has its own modulator. Yeah, right. So in this optical system here, yeah. So these are I think these are the calibration optics up here at the Gregorian optical system, right? That allow you to, they've modeled the mirror responses. They can, also measure that to compare. But each instrument has its own modulator, and so it'll have to do its own calibration as well for the instrument response.
Okay. Among the different influences, which has larger influence in the modulation, the rotator optics or the main mirror?
I mean, yeah, they're probably, so the rotation and all these optics with the folding optics here probably have a significant effect, right? But they're after these calibration optics. So you have a chance to well calibrate them and measure and figure out what they are. The M1 and M2, they're not 45 degrees, they're 10-degree reflections, and it sort of, varies across the mirror, but we don't have a way to actually do a measurement of what that polarization is, or what the, effects are, what the Mueller matrix is of that mirror. So the choices are, we can, calculate what the coatings are. We have samples, they have samples of the coatings that were actually applied to the mirrors, and they can, test those in the lab. There are some other options, include, if you look at a sunspot at disk center, you should have, a rough idea of what the polarization, the Stokes profile should be. It should all be, Stokes V, certain lines behave in certain ways. Another option is looking at 90 degrees away from the sun, where there shouldn't be polarization. And so then you can sort of calculate that, so having some sort of known input sources is another way to try to get to that, calibrate M1 and M2. Another thing I'll mention that they, that they've looked at is that, they have these polarization optics that they put in up here, and, they put them in the beam, we've thrown away most of the, 12 kilowatts that the primary mirror is collecting, but there's still a few hundred, on order 100 watts that are going onto the optics, onto those polarization optics. And so you put them in the beam and they heat up, and then the retardance is changing. So your polarization optics are also changing in time, which is another complication, and with the large aperture. Mhm.
Oh, and this is 4 meters.
This is 4 meters.
I remember once being in Gregor,
Mhm.
and we started to smell something was burning down in Gregor,
Mhm.
and we just burned down the calibration optics.
Right.
Okay, so
Because what did we say the other day? Or, we talked about what are these calibration optics? What is these polarizers often made of? Plastic, right? They're stretched, thin pieces of stretched plastic. So, their tolerance, they're obviously mounted between glass, and you can, reject IR and stuff. But anyway, these aren't, pieces of solid, strong glass. They're a bunch of components and coatings and stuff. So yeah, another challenge. And you go to bigger apertures, but yeah. I think so, yeah, these maps here, for example, yeah, I think they're about 10 centimeters across, so they're big, big pieces.
Just curious, does AO introduce any kind of polarization effects?
Not a lot, because it's, the reflection. So what AO is doing is somewhere in the beam here. Let's see, up here. Here's the deformable mirror. The only sort of AO picks off some light, and it measures and calculates what those deformations are. But the only sort of AO that's affecting the beam is this one deformable mirror that's in the beam. And that, as far as it's plotted here, it's a near normal. Those angles, it's, introducing very small changes in angles as that mirror is slightly changing shape. It's not really a significant time variation in that sense.
actually I think the deformable mirror is very fast moving.
Right.
So the main effect that you have when you have adaptive optics is basically the polarization. I think
The what?
it depolarizes a little bit, but very little.
Right.
But
No,
it doesn't change the Muller matrix.
Right. Mhm. Okay, let's take a break. Come back. How much? 10 minutes? Yeah.
Right. So we're getting started again. I think Michael wants to make a comment, and then Kevin will continue, and we'll get to leave early today after that.
So in full appreciation of this really very well-founded discussion of the accuracy and the various trade-offs, I wanted to give somewhat humorous a different perspective on all of this, because if you put an instrument that has cost $350 million into operation, it's a little bit like a battle plan. And so the targets that you want to study or hit can then be categorized in 4 quadrants following, now this is a very unusual source for me, Donald Rumsfeld. Because the quadrants are, there are the known knowns, which is basically you put your instrument on the penumbra and you want to see the Evershed effect. If you don't see it, something is really wrong with your instrument. Then there are the known unknowns. Those are phenomena which either by consideration of principal physics or by simulations, you know will be detectable now that you have this superior instrument. Next quadrant are the unknown knowns. This happened several times to me, that somebody showed up at a conference and presented something, and the reaction was, congratulations, you just found the solar cycle. So that's not a good quadrant. And the last, and I very seriously urge you not to forget about that, are the unknown unknowns. And that is when you have an instrument that really puts the physics phenomena that you study here on the sun on a whole new level. There is a discovery space. There could be something that you don't expect, but you want your eyes open for that and not dismiss anything that looks unusual.
Thank you for that.
Part of the challenge is knowing which quadrant you're in at any given time, right? I mean, that's who knows? Who knows what that one? No, unknown unknowns. Yeah, I mean, that's as I said, some of these, you know, some sense you design the instrument for some of the known unknowns, right? In terms of being able to do how well you can do your polarimetry. We think there's signals at, you know, 10 to the -4 that we can be valuable to measure, 10 to the -5, you know, but we don't know because we've never really probed those regions. And then we're going to get into, you know, unknowns and discovery space going to these sort of polarimetric precisions. Okay, so we'll be covering one last aspect of you know, big contributor to the noise, right, in our polarization measurements and how we deal with it. And that are the seeing effects, right? This is the other big part of the atmospheric effects. We have this level of atmosphere that lets us breathe, but you know, some astronomers, if you could just get rid of it and all wear scuba equipment all the time, maybe it'd be better. Live on an airless moon or something, because it really creates a lot of problems in our observations. It ends up mixing information sort of in space and in time, or as we observe in time. Some of this you'll see in the inversions. We have this sort of a fudge factor that goes into the inversion. Sometimes, you know, you have a multi-component model, or you have do an inversion where you're solving for two different atmospheres at once, right? And a big part of that is, you know, because you have a contribution from scattered light from areas outside of your pixel in your, you know, outside of the spatial area you think you're measuring, you have scattered light coming in. So you have another part of your spectral line is from different parts of the image. And so you need to sort of deal with that in the inversion, calling it a second component. And so some of that is, you know, from this smearing in the image due to the atmosphere. But it can also sort of directly affect our polarization measurements as we're trying to take them, right? And we'll see why here. So yesterday I discussed a couple temporal modulation schemes. So one of them is with this rotating retarder, right, that we talked about, where if I have a retarder and in the image plane and I rotate it, right, I see it'll modulate my Stokes Q, U, and V will all sort of be modulated differently. And some of these, at some points they go through 0, and at some points, they're maximum. And so by some combination of these, in this case, 8 measurements during this modulation sequence, you can combine these up in different ways, adding and subtracting, and you can get the QU, IQ, U, and V out. DKIS does this with 10 modulation states in a, in the same half rotation of the wave plate. I think Roberto yesterday was saying you could do it in as few as 4. You would still be able to do this, but the idea is the same. Over some interval of time, you record these different measurements, and you can get out the IQ, U, and V. We saw the same thing with the liquid crystals, same idea. I get a series of measurements, add them up in different combinations, and I can get my Stokes vector out. So that seems like it should, work and be great. But now what happens with, when I have seeing now, right? What is seeing? It's these sort of distortions that the atmosphere causes that vary with time and cause the image, to move in sort of random ways, right? So this is, you see all this sort of differential motion here. You see different parts of the field of view moving around. This is with a 6 hertz sampling. Let's see if this. So imagine I put my slit on here, right? This is, I have a slit across the image. And now at some points during this, while I'm doing that modulation sequence, I'm measuring one part of the sun. And then there's, some image motion. And now what's going into my slit is really from a slightly different part of the sun. And then I go to my next of those 8 modulation states, and maybe I'm sampling a slightly different part of the sun. And so, the Stokes vector that I'm measuring is not the Stokes vector from a single consistent point on the sun, but it's sort of moving around. And when I sort of add those up, right, if I had a strong Q signal in one point, one sampling point, and then, do that image motion a little bit, in the next time step or a few time steps later, there's a place where the Q signal wasn't as strong. When I add up I plus or minus Q, right, they don't cancel out properly, or they don't sum to the proper value. And so I'm not measuring the true Q, I'm getting some sort of noisy measurement. And, so this is at 6 hertz, so that's, fairly fast sampling there. Let's see if I can play that one more time. So, obviously that, this is with adaptive optics and, tip tilt correction. So these kind of motions are, certainly helped by having the adaptive optics. Adaptive optics basically was going to correct, a single point, single location in the field of view primarily, and there may be a lot of differential motion out at other parts of the field of view. So even, adaptive optics isn't, doesn't resolve all these problems. Multi-conjugate adaptive optics would help more. But even then there's some, those motions, even as those are corrected, there may be differential blurring. So that point spread function that's induced by the atmosphere will be changing. So I'm always going to have some kind of a little bit variation during my observations. I can even go, that was 6 hertz. We can even look, and there's image motion, even as I'm sampling. This is now a movie covering 2 seconds of actual observing time taken at a 400 hertz sampling rate. And so, these are, images are a few milliseconds apart, and already, you can see the slight deformations, the changes, right? If there's no, at a single point in the field here, do it again. You see the atmosphere inducing, blurring, image motion, and so on. So this will all, go into our measurement of the polarization, and we need to, figure out a way to sort of deal with this as good as we can. So again, there's my slit, my artificial slit, and you can see how the structures are changing, right? In the ideal case, this would be, perfectly constant over time. So people have measured what these image motions are, right? What is the amplitude of the motion, right? How many arc seconds is it moving? And I can, measure those motions and look at the power spectrum, right? How they change at different frequencies. So here at 1 second, I get the largest amount of image motion, right? We saw that sort of, and the 6 hertz, you can see there's a little less. And as I go out here now at, a few hundred hertz, the power is significantly down in these, different measurements at different telescopes and so on. And so you can see that things are better at higher frequencies. Here's just to show you the effect of adaptive optics. Here's a measurement of these image motions with and without adaptive optics. So without adaptive optics, you see the trend is you're increasing image motion at these lower frequencies. But if I turn on the adaptive optics, right, it much improves the image motion at those frequencies. Doesn't really help at high frequencies because, it's not operating fast enough to do these corrections at, several hundred hertz even. So you still have image motion at these high frequencies, even with, full adaptive optics. So, you can do another Mueller matrix and look at the crosstalk terms, right? Q to V, U to V, and so on as a function of frequency. Now you can calculate what those different crosstalk terms will be based on sort of what those image motions are and your sampling frequency, right? So I'm rotating my quarter wave plate at some frequency, and that'll interact with these things, and I'll see different crosstalk terms. More specifically, you can sort of calculate now what is the seeing induced crosstalk. If I have this rotating modulator that I have in my beam, right, and I can change the frequency of that modulator from, going around, making one cycle, half rotation every 10 seconds or 1 second or a tenth of a second, I can see how much crosstalk that will, these seeing motions will induce in my measurements. And so you see the crosstalk from Q, sort of we mentioned for this rotating, this is for the rotating quarter wave plate. It's very constant because it has this natural crosstalk effect, but the U and the V decrease as I go to higher frequencies in all these cases, right? And so, what this is telling us is that if I can rotate that quarter wave plate faster, I can reduce the amount of crosstalk I get in my measurements, because I'm taking these measurements as close in time as possible. If I can get those 8 measurements very close in time, I reduce my seeing induced crosstalk. So that's, and it changes significantly going, from 1 second, sort of where the peak of that image motion power is down here. It goes down by a couple order of magnitudes if I can get out to 100 hertz, right? So I really spinning that quarter wave plate really fast. This over here is the same thing, but it's done for modulation using the 2 liquid crystal polarizers. So again, you can sort of see the same thing. It decreases significantly over here as I go to these higher frequencies. It's a little better at some of these middle frequencies, but again, the same thing. Higher modulation rates are better. So I need to get all 8 measurements. I like to get them in a tenth of a second, right, or a hundredth of a second. But we just talked about how we need several seconds of integration to get these, high signal to noise rates, right? How do I get 10 to the minus 3 collect, 10 million photons if I'm trying to rotate my modulator and get all 8 measurements in 100th of a second. So the point is that as long as each of those modulation cycles, if I can acquire those 8 modulation measurements within, some short period of time, I can combine them, and then I can add up the combined sort of combinations of IQ, U, and V, and I won't introduce additional seeing crosstalk, right? So I can take my 8 measurements and sum those all up, and as long as I'm getting them all series at that rate, and then I can sum up as long as I want to sort of build up my signal to noise without introducing any of the seeing induced crosstalk. So, we don't want to, we want to take all these data very fast and then integrate for a while, right? So we don't just record for 8, 1/2 of a modulation cycle. We record for, a dozen or 20, right? As many as we need to build up that sort of, the integration time we want. So we don't want to record the data though, right? We're running at these high frame rates. If we're doing 30 hertz or 100 hertz, say, we don't necessarily want to record all those data and save all those images out to our storage. So we can sort of sum, take all those measurements and sum them either on the camera, say, or, in the computer before they're actually, keep them all in memory, cycle them out, and then go through and sum those in the memory, and then write them to disk at the, after I finish my total integration time of several seconds or however long I need. So actually, the frame rate I need out of my camera is high. I may need to run a camera where it's acquiring data at 100 hertz, but then the data rates that are actually being written out to disk end up being much, much lower. And there's some, very specialized sort of approaches to doing this, where you actually can even, to get even higher frame rates, you can basically sum on the chip. And so you're sort of moving the charges on the chip and not actually reading out the detector, but you're doing a modulation of which bin your data, your photons are going into, and even doing the modulation on the chip itself. And there's some things like Zimpol and FSP that are able to run at even beyond 100 hertz, at several hundred hertz. So that 400 hertz camera is one of the, that sequence I showed at 400 hertz was taken with one of the FSP cameras that can acquire data at these very high data rates. And so, that helps beat down that seeing induced signal to noise, and, allows you to get these very high, keep that seeing induced noise down and really keep it limited to the photon shot noise. So, another aspect of this is, we're talking about temporal modulation. We can also do, a spatial modulation or semi-spatial modulation. And, we mentioned this a little bit ago. We have these, what comes out from my analyzer is both an I plus and an I minus sort of combination, or some combination of the Stokes components. And if I, put in this polarizing beam splitter, and I can get both of these at once, either on 2 different cameras or on the same part, 2 different parts of the same camera. And so that way, if I have I plus Q and I minus Q at the same time, right, they're both recorded with exactly the same seeing distortions. And so when I do that linear combination, adding them up or subtracting, I don't have any sort of seeing induced measurements in that. And so, this is very important. In addition to preserving all the photons, you also, help reduce the seeing induced noise. Now, and the example, someone, tested this, comparing, a single beam measurement with a dual beam measurement, right? And you can see that there's a lot more noise and crosstalk in here, where there's a lot of Q and U here, and then other crosstalk even here in V, right? All these sort of spurious signals. So, this is important, and almost every polarimeter uses this dual beam, obviously, for a variety of reasons. Now, of course, the dual beam, I called it, semi-spatial, because it's only gives me, two of these samples at once, the Q and the U at once, but then I have to record other measurements to get the other Stokes polarization states. And in practice, I'm not really, some of these, even in that rotating retarder or with the liquid crystals, I'm not recording pure I plus and minus Q, right? I'm taking a series of measurements, and they all need to be combined in order to get the final response there, right? Go back, please. Here I need to combine multiple measurements. So even though I'm getting two of the measurements at the same time, it doesn't fully solve the seeing problem because I need to combine, more than just two measurements. And, it is possible that, you could design a system that could record multiple measurements, all, more than two measurements at one time. Turns out a lot of times it doesn't quite work out as well as one might hope. The optics get much more complicated. So in practice, most systems just use the two beams. The other thing I'll mention about the two beam approach is, right, I have, when I'm combining these two, right, I have to add or subtract these two, the plus and the minus beam here. They're going on to two different detectors, right? And going maybe through a little different optics, right? This one's reflecting off, here, or going through a different part of the polarizing beam splitter. And so if there's any sort of difference in the calibration of these two detectors in the flat fielding, when you add and subtract these things and you're trying to get to the 10 to the minus, 3, 10 to the minus 4, your ability to actually flat field your detector to that precision is really hard to obtain. And so what can be done in practice is, with my polarization, the modulator, I can switch these two. So I take one measurement where I have minus and plus, and then at with a different setting of my polarization modulator, or a different angle of that rotating retarder, this now becomes plus and this becomes minus. And so then I can combine all four of those measurements to both eliminate the seeing induced crosstalk, but to also cancel out any calibration differences between the two detectors. So, it's a very useful and powerful technique. So this was, a limitation of having a slit, right? I have a slit and I need to get these measurements all at the same time. As we saw yesterday, these liquid crystal retarders that we use in imaging spectroscopy, they don't generally run at hundreds of hertz, right? And so we have to sort of, they won't work to try to get these, for imaging spectroscopy, to try to get these very high frame rates. But we have another advantage that we can use in, for doing these images, right? And we have spatially resolved full images instead of just the slit that we're measuring. And that's, we can do what's image reconstruction on our data, right? And so this is an example of, I was showing before, where I sort of have this, the image, and it's changing rapidly in time, and this would induce seeing or induced crosstalk. But since I have the whole image, I can, calculate what these motions are across the field of view and apply corrections. And now my, what I'm measuring is much more stable. I don't have as many seeing effects in my final, output image. And I can do this before I do this combination of the different modulation states. So I can remove the seeing effects from my images and then do my demodulation and combine the different modulation states, and I can eliminate a lot of the seeing induced crosstalk that way. You can even go a step further, right? And this is an example, not that you'd want to do polarimetry in H alpha, don't advise it. I have done it, but still don't advise it. So this is an example of we take a series of images here in of the same scene, right? And then I can apply what's called, a variety. There's different reconstruction schemes where I can use these multiple images and get out a fully speckle reconstructed or deconvolved image of that scene, right? Where I've taken out both some of the blurring from the seeing and the telescope PSF. So I have, a fully diffraction limited image over the entire field of view. So, with the slit image, what I'm getting through the slit in my spectrograph, I can't really do that because I only have this, small, area of the sun. So I can't really deconvolve because I'm losing some information. I don't have enough information coming through the slit to tell me what was falling on the slit. But I can do this now with some, full image reconstruction on my images, again, before I apply the demodulation and combining those different modulation states. And so I'm basically have diffraction limited images that I apply, I demodulate. And so I get, I remove a lot of the seeing induced crosstalk that way. So, as an example of that, I think what's sort of the extreme polarimetry with sort of a Fabry-Perot imaging polarimetry instrument was done by Francisca Zurnier where she did some deep imaging here. So just in a few wavelengths and with fairly long integrations of just the quiet sun at the center, at disk center, and applied these kind of corrections. And so now you see the QU and V signal here, is very small. These are scaled to plus or minus 0.3%. So there's not a lot of crosstalk here. But by combining a lot of images, she was able to pull out the scattering polarization signal here at disk center, both the Q and U, right? And interestingly, right, the Q is sort of aligned this way, just because of the, that's the scattering direction, and sort of washed out here, but the opposite direction, or the 45-degree direction for U. But again, so this is, taking, integrating for about 30 seconds, I think. But now the amplitude of this Q signal is just, a few times 10 to the minus 4. So, even with an imaging system, right, we're able to do polarimetry here at 10 to the minus 4 and get recover the full map over the field of view. So, it is possible to do this deep polarimetry. Often, there's sort of, the way these instruments are used are different. We use spectrographs because they sample the whole line at once. You can get this sort of 10 to the minus 3, 10 to the minus 4 polarimetry pretty well. They don't need to, you can integrate for long periods without, reducing your spatial resolution too much. But anyway, so, the deep polarimetry is often done by spectrographs, whereas imaging polarimeters, we're still hadn't achieved this level of polarization accuracy or precision. So, we can do this sort of image reconstructed polarimetry, and we can, get high spatial resolution and get precise co-alignment that, takes out a lot of this crosstalk. We still need, pretty short exposures in order to freeze the seeing and get these sort of individual snapshots of the seeing condition and preserve as much of the spatial information as possible. You often need lots of these images in order to do the reconstruction. You're using the fact that you sort of have multiple realizations of the same solar image. And, by comparing those, you can sort of separate out the seeing distortions from the underlying image. So you naturally take multiple images, which gives you good signal to noise in the end. So that's good, sort of compatible with polarimetry in that way. the one problem is, unlike the case for with the spectrograph, where you can just sort of demodulate in real time and add up all your images and get your, a final spectrogram out at a fairly low data rate. In this case, we need to record all the images before demodulation, because we have to do this image reconstruction, the post facto image reconstruction first, and then we need to demodulate. So we need to record every image. So we were running at these sort of high frame rates, similarly high, on order, 30 frames a second, but we need to record those all and store them, and they're processed later. So we end up, this ends up being very data intensive in terms of, terabytes of data now with DKIST. So we have 4K by 4K detectors, and they're running at this 30 Hertz. And so, it is a very data intensive and then, computationally intensive sort of approach. But it is a, sort of a different way to do the polarimetry and, compensate for this, these seeing induced effects. I think I'll, stop there, see if there are any questions. Might be on, hold on.
Image reconstruction of that H alpha. How do you know that you have not overdone it?
I always. So yeah, I mean, it's a concern, right? The speckle reconstruction is using some assumptions about the statistics of the atmosphere, and that it sort of follows a Kolmogorov turbulence spectrum in the atmosphere. So, it has some assumptions baked in, and if it's not correct, then it's you could overestimate it. We have done comparisons between an image, a speckle reconstructed image, and a simultaneous image from Hinode, right? And we can look at the power spectra of those two and see that, in that case, and that realization of the atmosphere is, fair to say, it properly reconstructed the power spectrum out to, the sort of the diffraction limit or close to it. So it works in that sense. In this,
with the tiny caveat that Hinode doesn't have the same resolution.
This is, I mean, this was done with the Dun, or that comparison was done originally with the Dun. So it's a 76 centimeter versus a 50 centimeter. So there is a difference there. But it didn't do too many bad things to the power spectrum. I mean, was good to see. And so hopefully, in that sense, it seems to make reasonable assumptions, right? The other thing you can do is, instead of making those assumptions that the speckle does, you're going to apply a blind deconvolution technique, which puts in fewer assumptions and just tries to use a sort of a least squares approach to finding the best fit, separating out the image and the distortions, and you get similar answers in that case through a very different process.
Time scales at the times. That the time scales that you are correcting for are very different than the solar ones. That you don't eliminate any solar ones, right?
Right. That's another reason you need these high data frame rates, is because the same problem we're discussing with the trade-offs is the solar scene is evolving, right? And the underlying assumption in these is that you have the same solar scene and a changing atmospheric distortions. So you need to get all your observations in that short window before the solar scene might change.
I don't have a question, but just a comment about your last slide that we are ending up with the lots of data.
Right.
So just I wanted to mention that the observations with SSC, even in 10 days, we ended up with 100 terabytes of data. And then after that, that has to be seen and reduced and checked that which is good, which is bad. So just a comment.
Yeah, no, I mean, it's a, yeah, I mean, I think it's a powerful approach to do this, but it's really, it's pushing the data volumes as far as you can, right? You know.
To go very fast with your polarimetry analysis. You made the example of simple and so on.
Right.
But those frequencies, don't they depend on the spatial resolution of your observations?
The frequencies.
Need to go.
Yes, I mean,
Yeah.
yeah.
Also the
Tied up in this is also, you know, what's happening is you have these, you know, image motions, right? And if it's a 1/10 of an arc second, but you're using a small telescope and you only have a 1/2 an arc second resolution, then even, you know, these small image motions won't change a lot in what is under your slit or what you're measuring at any given time, right? And so, okay, I moved by a 1/10 of an arc second, but I can't resolve that. My telescope hasn't resolved that anyway. So it doesn't have a big effect. A 1/10 of an arc second, if I'm using VISP and I have the, you know, 0.04 arc second slit, 1/10 of an arc second is moving something completely different, a bright point in one, you know, one part of my modulation cycle, and then I'm off on a, you know, something else, maybe a granule or something in the next one. So, and I'm resolving those completely. So yes, it does, you know, it could be more of a, it gets to be more of a problem if the resolution is better, or if the contrast is higher, you know, in your image, and the intensities are changing, right? If I, you know, it's in the middle of a sunspot, well, that's not even a good example, where the intensity doesn't change much. It may not have as big an effect because the structures are, you know, very similar maybe, but if it's, you know, a place where I have a bright and dark features nearby, and then I'm moving, you know, the slit is moving or the scene is moving under the slit, that will introduce more noise. So it's all tied up in, yes, resolution and what the structures you're observing are. So this is sort of indicative, but of what the noise is, but can't fully characterize it for any given observation. Anything else? Otherwise, we'll get out of here early and or there.
Yeah, we are done. I just want to make sure that does everybody have STR installed? We're starting tomorrow. Good. Class dismissed. And I'll go home. Thank you. Thanks, Kevin. Hopefully Carlos will make it. Actually, we'll start with David first.